How's it going? I gotta get a quicker start on these streams. I'd like to be on like a good hour or two earlier, but we move slow once in a while. We move slow. But here we are set, and we have a pretty concrete set of stuff to get done today. Oops. Cool. So, where we left this off yesterday, why am I sitting in green haze? Like, do I have to make this any brighter? Really? Alright, fine. I'll stare into this all day. Sure. Um, so where we left this off yesterday, we had some pretty good progress. Where the heck is this? Bufferlib, environments, ocean, MOBA, and then MOBA.h here. No, MOBA.c. Okay, so here we were implementing a few different layer types in C here. So we have this LSTM. We got the full implementation done, but it needs to be error checked and the like. We also have the conv done yesterday. And pretty much all I have to do is finish this today, make sure that this is correct. I have to write some sort of better test on this, and then probably from there, we're going to figure out a way to clean this up a little bit so we can have like a portable little standalone. And then we'll go from there. But that should be enough to get our RL models onto the web. For sure. Let me remember where we were, how we were doing this. Hold on. Right, so we have this here, where we can look at the individual weights in the LSTM here, right? This is garbage, right? Oh no, that's old. Okay, here it is. Yeah. So we have our breakpoint here. And then here we're going to need to put a GDB breakpoint of some type, I assume. And we're going to have to look at the individual outputs of stuff. Right? Yeah, I think that's where we left off. So in order to do that, let me see where we want to start. Probably like here, 103. And then, hold on, export. How you doing? Doing well, thank you. Oh, thank you for making me notice. I have to rearrange this a little bit. We are doing some cool stuff. At least this will be cool when it works because we'll be able to run really nice networks in the browser. Okay, so here we are in the start of the LSTM layer, right? And then I run this flatnet thing. And we have this buffer. So let's see if the linear layer is correct. Do you stream daily? Usually like 5 days a week, Monday through Friday. And then I do solo dev on Saturday. Usually somewhere around 1 p.m. Pacific to like 8 or something like that. I've been trying to get on earlier. I don't know, just me being lazy, taking too long to like get my exercise done and get food and all that stuff in the mornings. Okay, this gets saved into buffer, right? So oh, there you go. You can see right there that we match here. And like if I do buffer of 10, this matches. And now we should check to make sure that this is correct across everything. So like, I don't know, 1024, which is 20. Yeah. Isn't it difficult to reply to chat and focus on the game? What game? Game here is writing code. Are you a language model? Is this an automated bot? Say something if you're actually a person here. Heh. Twitch bots. That's so obnoxious. Well, our linear layer is correct. Hi, sir. Welcome. Hold on, let me ban this bot. There we go. Literally an advertising bot. Welcome back. Okay, so this is now at buffer, right? And we should be able to see like, oh, that's going to be hard to figure out if this is correct, isn't it? Yeah, this is all 1. Okay, we'll have to do something about that. Yeah, all of these gates are all 1. I think we need to just like divide by 10,000 or something in all of our input data. Yeah. That's obnoxious, but at least we know that our input layers are correct, right? Yeah, so just all of these places where we are doing A range, let's just do over 10,000, over 10,000. Oops. And this will get us into a data regime where essentially these sigmoids and these canhs, these functions here, will not always give the same result. We should actually be able to get something done there, I would hope. That might actually still not be enough, but we'll see. Because all the weights are positive, right? Wait a second, all the weights are positive. Well, we'll see what this does on its own. Welcome, YouTube folks. We're currently fixing the LSTM layer here. And we're testing to make sure that this performs exactly the same as PyTorch. So what we're doing is we're getting a little bit of synthetic data, and then we're going to test to make sure that at every portion of this function, we match the PyTorch reference. Okay. Recompile this. Where'd my commands go? Cool. And now 103, we have buffer 0. And here we should have buffer, oops, 0. And these match, as you can see. And we can do like buffer of like 1024, which I believe corresponds to buffer 20, and these match exactly. Perfect. So our linear layers are correct, as we suspected. 20. So now we go down to the bottom of the gates, right? And perfect. So now we actually have applied the gates here. What are we searching for today? Yes. So the goal here is to get these models, which is, hold on, let me show you. So I have this this MOBA that I've been coding for RL work. You can actually play it online here. This runs in a browser. You can like run around. You know, it's a basic little MOBA. Here's a speed buff, right? It's got like an assassinate ability on stuff, and so on and so forth. Yeah. So, and what we're trying to do with this thing, if we go to the GitHub here, we have these models that we're using for the RL agents, and they're all pretty similar. They all are going to use convolutions. They're going to use linear layers, a few activations, and an LSTM. So here's the network for the MOBA. So basically, if I can just implement all these layers for in C, I'll be able to compile them and run them on the web. Hey Noah, how's it going? We're porting models to C so that we can run them online. Speaking of which, if your breakout environment is done, we should get that integrated because we're starting to have some cool demos around here. Here's the MOBA being run in browser, right? Lots of cool stuff going on. Well, that's what we're doing for the time being here. And it looks like it's going fairly well. Five, 1, 3, 9. Yeah, that's correct. No time to work on it. Start next month. Sounds good. Yeah, Nathan is also currently writing his thesis, and he says he's going to be working on some cool environments next week. So, cool stuff. But for the time being, I will handle all these nets, and we'll actually be able to run stuff on the web, which will be very cool. Let me see how I want to check this. So, hang on, I times hidden size. Wait, buffer. Right. So this buffer is of size 1024. Let me just make sure I understand this. Yeah. Yeah, okay. So I here is 500, was this 128 elements? And then, yeah, this is correct. And now we need to check. I mean, the other ones should be right, shouldn't they? Like if I do buffer of 120, of what is 0, 128, this should be, well, not buffer, it should be I here. I'm getting confused with indexing. Okay. F of 0, 0 should be buffer 128. Is that not correct? Sigmoid of F. IFGO. Did I mess this up somehow? Let me see. IFGO is split the buffer. And then I... Did I get the dimensions wrong somehow? 16 by 128. I might be interpreting the dimensions wrong. Because we just put a breakpoint down to here, right? Wait, does this make sense? No, this logic is wrong, right? 2 times hidden size. Wait. Batch offset is 4 times the batch times the hidden size. And then you do the buffer address, B offset plus I, equal to sigmoid. That looks good to me. Okay, maybe we figure something out here. Buffer of 1. This matches. This also matches, right? About 127. Also matches. What's I of 1, 0? 0.5087. Is that correct? I guess it would be. So F of 0, 0 I fail to see how this happens. Hmm. 128 is equal to 0.5. Somehow these gates are not lined up the way I think that they are, I guess. So what I think should be happening here, right, is that there are 4 different gates. You can see them here. I, F, G, O. 4 different activations, I guess. And these are each 128 dimensions. So I want to check that the values that are computed in C for these are equal to the values in PyTorch. And it looks like the first set matches and the second set doesn't, which is very bizarre. Because literally I just go through and set the first however many this is, right? Torch.sigmoid of F, right? You split it into size of hidden chunks, yeah. And we know that the sigmoid function matches because it matched for I. So why does it magically not match for this? What am I not seeing here? Sigmoid buffer, buff address. Offset is equal to 4 times the batch times the hidden size. This is 0 for the first loop, right? And then hidden size is 128, so this is the first 256 elements. And then you just go through 0 to 256. You set the buffer equal to a sigmoid here. Let's rerun this. So buffer 0, 28, right? 0, 0, 0, 128. Oh. Well, hold on. Match is there. But 127, you get let's just take a look at what our data is here. Maybe the test case is weird. Because there's nothing that should go, like, should be cyclical like that. Oh, wait, am I just not, hold on, num buffer. Input is num input. Buffer, num buffer. Output, num output. And we have hidden size. The weights input. This should be 4, shouldn't it? 4 times hidden size. Yeah, so the test case is just wrong. So we have buffer of 0. That's a little suspicious. Oh no, wait, because it's already, yeah, this is fine. So, okay, so I still matches. Let's check 127, which is buffer 127. This matches, which it did before. And now this looks better. This looks way better. Because if I do... This doesn't work here, right? Because it's F 0, 0. 9, 3... That's a little bit off. 9372. I don't know if that's within numerical precision. I would doubt it. Yeah, no, in the third digit, I don't believe that. Let's check the next one. What copilot are you using? Super Maven. It's great. I highly recommend it. It gives me very fast one-line completions, which is all I want. It'll do multi-line as well, but typically I just want really fast one-line completion. Save typing, not thinking. Okay, so something is screwy here because... Do I believe that it's that far off? No, I don't believe it's that far off because if you look at the 127th element, 9359, 9359, they match perfectly. Plus, this is 0 to 1 data is where the high float precision lives. So what happened here? Are you essentially flattening arrays? Kind of, yeah. I have, on the right side, I have a PyTorch implementation, which is like just going through the different operations in the LSTM. And on the left, I have GDB over the C implementation that operates on flat buffers. And I'm trying to make my C implementation match the PyTorch implementation exactly. Because if it does, then I can load weights from pre-trained PyTorch networks into it, and I can run them on the web, because I can compile the WebAssembly. And then I'll end up with like this 300-line file that lets me just run whatever I want on the web. But, you know, you have to get them to match exactly. Is Super Maven free? There's a free version, but I highly recommend the paid one. This is very weird because it looks like the sigmoid should be good. Are my weights somehow being set differently? They shouldn't be. We should probably make sure that the linear layers match before we commit to all this, right? So here, buffer 0, buffer 127, buffer 128, right? And I can do buffer 0, 0. That matches. 27, 6, 8, 1, 7. Yep, that matches. And then 0, 128. Okay, this does not quite match right here. So it might not, it's probably not the error in the gates. It looks like there's something wrong with our linear, which is very weird because we have that tested independently. So I think that what we're going to have to do is we're going to have to make, first of all, we got to make sure our test data is actually what we think it is. It's actually the same. And if it is, then we'll have to look at the linear layer, because maybe I missed something earlier. I didn't think that I did, but we'll see. Welcome to all the YouTube folks. Oh yeah, by the way, very quick plug. All this stuff is free and open source in Pufferlib. All the RL stuff. We're 16 stars off of 1K. So if you want to help me out for free, star the repo to feed the puffer. Thank you. Back to dev. Maybe too basic. Too much data, difficult to print. Start of each your segments aren't included. Well, that's what I'm doing, right? I am doing that. That's what I'm printing out these elements here. I'm just doing it interactively is all. You know, because it's obnoxious to write test scripts that are like across Python and C at the same time. I'd have to write bindings. Well, they definitely mismatch here though. So let's take a quick look at the, we'll look at the code side by side. Okay, so here's the code in PyTorch, and here is the code in C. And we're going to want to look at the data going into these to start with. So this is where I make the test data. And then let's see what I do over here. So input, num input is batch size times input size. These shapes look good. And then the state data, batch size times hidden size. Num output, batch size hidden. Yep, that looks good. And then buffer is 4 times batch times hidden. Just hold on, are the weights wrong? Wait, 4 times hidden times, no, that's correct, right? 4 times hidden times input, 4 times hidden times hidden. Yeah. Right? Oh, look right here. It was just ever so slightly off because we forgot to add the test data to be the correct shape for the bias. Hey man, what are you up to? I'm currently making this C implementation of ConvNet plus LSTM match the PyTorch version so that we can compile it to WASM and run it on the web. So that we can actually demo our cool RL agents online. I bet it's going to match now. Grab some sample points. Oops, buffer 0, 0. Matches perfectly. We didn't do 1.7. Matches perfectly, right? Down to the last significant digit. Perfect. Now it matches. Okay. So now we are at, we just went past the activation functions. So where's the PyTorch math on this? I mean, if I just look up the docs, I'll show you what part we've been doing. So we just confirmed that all these map moles are correct in here, all these args, and now we're going to do these individual activations. We're going to make sure that the code is correct for this. Nice to catch you live. Welcome. We're doing some crazy stuff today. Okay, so the first element matches here. Let's try 127. Matches. And now here, I have it organized a little differently, so it should be 1, 0. And then this is going to be buffer. It's flat, actually. 512. Matches. I've had good experience using Onyx. I tried Onyx, and it didn't work. It was a pain. So if you have an easy way to get this working with Onyx and C, I'm all ears. But I have not found an easy way of doing it. There was like a massive chain of dependencies and build and shit. It was such a pain that I was like, well, I can just write 300 lines of C. Like and subscribe because it's hard work. Yeah, thank you. And honestly, like, folks, just star the repository. We're so close to hitting 1,000 now. 984. New to ML stuff and only started my first research project surrounding the topic a month and a half ago. Think you can join a competition surrounding degenerative lumbar spine disease. More experience in the field on a high level. What would be your steps to tackle? Is it just testing, CNN, VIT implementations, and doing param sweeps? Well, it depends how much compute you have access to, right? A lot of stuff actually is going to depend a lot more on the data than on the models. So you definitely are going to want to spend more. You're going to spend a lot of time massaging the data. It depends how much of it there is as well. Usually with stuff like that, you don't have that many images or that many samples of stuff. So yeah, that's usually you end up spending a lot of time on the data. Like architecture will matter a little bit, parameter sweeps will matter a little bit, but probably just getting better data is win. Or like figuring out like ways to augment the data or something like that. Okay, so here, buffer 128, I did it on JS on phones. Yeah, if you want to do it with JavaScript, then sure. I was looking for a C API to Onyx, right? Because like if I do it in JavaScript, then I have to figure out how to get the stupid like actions from JavaScript back into the C environment and stuff. It's just such a pain. All the like multi-language stuff. This is gonna literally end up being like a C file that just works. Yeah, like people will see this and they'll think I'm just memeing, like, why the hell are you doing this in C? And it's like, no, I'm not. I'm doing this in C because it's literally easier. It's literally easier. And like doing this is kind of cool. Like make it like trying to get this shit working in the JavaScript ecosystem is going to make me demonetized, right? Let's check the tanh gate. Is the whole tanh gate going to be like this? Ah, shit. So the whole tanh is like this? Really? Yeah, because the numbers are too big. Tanh goes to 1 very quickly. I think we have to scale the data down a little bit more in order to make sure that we can test this correctly. Thanks for the answer. Comp does mention using other publicly available datasets is allowed. Haven't thought of much regarding augmentation. Train a new model or an existing classifier for an unrelated but similar type of class. Probably fine-tune something. It's kind of difficult when you don't have compute for stuff, right? It's just like, it's so much harder to do anything in these spaces when you have big models that actually require compute to train. We're going to add a 0 here. And what this is going to do is this is going to get us into the regime where tanh will not just always be 1. So we'll actually be able to test to make sure that we match correctly. He's not joking. Writing it in C is literally easier. I'm not doing this just because I'm a masochist. I'm not denying that I'm a masochist, but like, I'm not doing it just for the sake of masochism here, right? I have limitations there. It's because it is actually easier. Honestly, this is pretty comfortable. Let me make sure we didn't mess anything up. Whoops. Okay. That's good. And now we need G00, which is going to be buffer 256, right? And does that look good? I think so. The precision is a little iffy. Yeah, no, that's definitely correct. So perfect. So now we know that these layers work. Let's just to be thorough, let's do like 384. Uh-oh. Wait, did I do this wrong? No. FIG. What's the other gate called? Is it O? I think it's O. There you go. Okay, so all the gates are good. We now know that the LSTM implementation is correct all the way through to here. Oops, through like to here. Now we just need the last 2 lines of it. Currently learning DSA. Domain. Domain. I literally don't know what this is. I literally don't know what this is. You'll be very surprised about like the number of standard things that I just don't know what they are or haven't used. Oh, okay. Well, that one is definitely useful. I'm not a fan of teaching beginners JavaScript frameworks, but yes, core data structures and algorithms you definitely need to know. I don't know if that's a specific book or just like the abbreviation in general, but yeah, your first course in data structures is very important. It's actually very funny. I think that if I wanted to apply for like a traditional software engineering job, I probably would have been more qualified by interview standards after my freshman year of undergrad because like they just ask you all the random basic data structures crap and you don't remember the stuff like the portions of that you don't use for 10 years. I see. I mean, Stanford, we just have course numbers on stuff, right? Please guide. Trying to train a custom AEC 2-agent environment. Oh, AEC. Okay, yeah. 2-agent environment. By AEC, you just mean turn-based. Observation space being the same, and the actions being different. Would you be willing to point me in the right direction? Geez. So, yes. Um, I can show you how to hack it. So, here, most things don't handle AEC. I can make that work with Puffer. Um, action spaces being different, basically nothing supports correctly. So you're gonna have to like pad your action spaces or whatever in like an environment wrapper. Um, with Puffer, there is a mask output, an optional mask output that you can return. And what you will do is you'll basically just set the mask to like mask out the agent whose turn it isn't. Does that make sense? So you can just mask out whatever agent is not that doesn't have their turn currently, and then Pufferlib will just work. You will still have to write a wrapper though to like match the action spaces. That is one of the very few features that I haven't done in Puffer, and like it's a real pain to do that. Like it's very very difficult to do that efficiently without messing up the whole rest of the stack. Welcome as well. Can you explain what Puffer is? Mm-hmm. So, I mean, broadly speaking, Puffer is my attempt to fix all the stuff that's currently wrong with reinforcement learning. So it contains a bunch of different stuff, but the high level of it is from the iceberg video, which I'd recommend if you haven't watched that full thing. Um, it's generally low level tools and infrastructure to make it easy to work with lots of different types of simulations and to do very fast simulation as well as fast parallel simulation. On top of that, we have like sane training libraries, sane training integrations, nice hyperparameter sweeps, and other utilities that just make it really easy to automate a lot of experimental research work. So that is what Puffer does. Um, iceberg vid openable watch. Yeah, the iceberg vid will really do a better job than I can do just off the cuff here. Um, I mean, that video, I made it for this reason. It's like 26 minutes for a complete overview of the whole stack of reinforcement learning, my thoughts at every single layer of the experimental and infrastructure stack, and what I am currently doing about it in Puffer. What you're watching right here is a very specific small portion where I'm looking at fast environments, and I'm just porting a couple inference things to see so that we can run demos on the web, and so that we can have like nice self-contained stuff. But yeah, nice haircut. I did not get a haircut. Nice try though. I was going to go get it cut. It's too long. It gets in the way running. It's too darn hot outside. Well, we have the LSTM matching up to the gates. So, what do we think the odds are that if I just put a breakpoint at the end of the function, that this will work? Let's try this. Did you try just copy pasting code to an LLM and ask it to convert to C? No. That route leads to much pain and suffering, because I would rather just write the code than and like spend my time understanding the things that I've done wrong and fixing those, rather than not writing the code and spending the same amount of time fixing dumb bugs that an LLM has written, where I have like no understanding of what the hell it's trying to do. I generally suggest using language models to save typing, not thinking. $214. Okay. So we have, is there an output here? Bias, buffer. What is this thing writing into? Wait, what the heck did I make this thing write into? Oh, state C, state H. That's fine. Pain and suffering, GPT report. Yeah. View on LLMs is refreshing. God, are the answer? It's not. It's really not. And it's mostly dumb junior developers who think that they can, like, get out of learning how to code. It's a really, really dumb thing to be doing. Like, here's the really obvious way of putting it, right? Like, if you think that you're gonna have value just by typing prompts into an LLM, like, everybody can fricking do that. Okay? So, yeah, you're potentially right now in the next couple of years, maybe you can build some cool applications and make some money, but like thereafter, you will have zero skills and zero value whatsoever. Like, you're guaranteeing that you will replace yourself, not because the AI is good, but because you have literally zero skills. That's like, this is why I suggest not doing this. Yeah. It still will write tons of bugs converting languages. I tried that before, um, with some C code, and it was worse than me just writing it myself. Because like here, this is how you use language models to convert code faster. I use Super Maven. It gives me one line autocompletes. So basically, I'm tabbing one line completions, making sure that each line is exactly as I want it. So it's like I can type 200 WPM. I'm still doing all the thinking, but it's like I no longer am limited by me only being able to type 80 WPM or whatever. And I get like a 30-40% productivity boost out of it. That is what I recommend. That is how you actually use AI to increase productivity without rotting your brain, basically. Few written in Python. See? Wait, did I miss a message? Did I miss wait, I think I missed a couple messages here. Would it even be smart to do that? Is it possible? Okay, I missed some stuff. Is it possible to build the environment entirely in Puffer, or should I use Petting Zoo and wrap it with Puffer? You can do either. Puffer supports Petting Zoo and Petting Zoo Parallel API, mind you, and Gymnasium natively. So we have support for that. There's also an advanced thing you can do with Puffer if you really want extra speed. So like the new environments I'm working on use the advanced API because we want 1,000,000+ steps per second per core. My environment is very simple. It depends how fast you want to train on it, right? Like even for very simple environments, I can get simple environments training at over 1,000,000 steps per second. So when you can do that, you can basically automate everything. What is the mini-grid env? I'm trying Pufferlib for the first time. If you look up mini-grid, it's like a commonly used, very simple learning benchmark. We have integrations for that. We have Atari, we've got ProcGen. I mean, there are like a dozen plus standard environments with Pufferlib bindings for it. We basically, like, we have all the standard stuff in Puffer. Our goal is not to make your life more complicated by introducing a bunch of new stuff you don't need, right? We have all the standard tools exactly the way that you'd want them, and they're faster than the alternatives. That's what Pufferlib gives you. Now, if once you've done that, right, if you want to go a little bit deeper, if you want to use our custom environments, if you want to write ultra high performance simulations in order to make your research or your work, even if you're in industry, go 100 times faster, we have stuff for that as well. But it's not required. You can get benefit out of Pufferlib immediately without having to learn basically any new stuff if you've already done a little RL. And in case there are any industry folks here, we do have support packages. Copilot is fine, just don't use it to write huge chunks of code for you. Let's see. Is this right? 153? That looks good to me. Let's do like 129, which should be, I think, like 1, 1. Well, that doesn't work. Oh, 1, 1. Yeah, okay. So this is completely correct, which is kind of cool. Let's do like, what's this, 257? No, not, yeah, that's perfect. Joseph had trouble with pip install -e dot on dev. I probably broke the MOBA build on dev, is what probably happened. Is that what was it? Is that what it was? Yeah, okay, I'll fix that. My bad. Let me fix this thing here. It's just I put it in the same file. I should have made a different file. I am allowed to break things on the dev branch. You can yell at me if I break things on like on the stable branches. On the dev branch, this is how it is supposed to work. If I break a thing by doing dev fast, you just come here and tell me. I will fix that as soon as I finish checking this one little thing here. I want to contribute and want to break some stuff. Great. Let me let me just open real quick. For folks watching, if you're like either maybe new to reinforcement learning, new to ML as a whole, whatever, as long as you have some development experience, building some cool RL environments is a really good way to get involved. Now, you can, of course, make contributions to the infrastructure and stuff. That's a lot harder. But if you're just looking for like a fun way to get into some RL, let me see if I can find some of these environments in here. Some of you might be familiar with this. Somebody's been building like a ultra high performance clone of this old MMO called Dofus, the combat system from it for an environment. We also have a few Atari environments that people have been making. So like, I think Noah might even still be around here. He's got Pong. No, he's got Breakout. And then, let's see. Yeah, so here is stupidly high performance version of Pong. We're going to try to replace some of the Atari environments. Here's like stupidly high performance version of Breakout. Goal is going to be to replace tons and tons of environments with ultra high performance versions. Train and evaluate on minigrid. Looks cool. Seeing the agent complete the tasks. Yeah, it should. It's that's a pretty simple task set. Also, minigrid. That is it would probably only take me a couple days to restructure the grid environment that I have to do all of minigrid at 1,000,000+ steps per second. Probably could get more than that. Scythonizing Spatian from Ocean. You'll bet. That's a test environment. That one doesn't have to be any faster. That one's literally like a 10-second test environment anyways. Like, if you want to be building stuff, like, build some cool game environments, right? Or other types of environments, right? Just, like, build some cool high-perf simulators. Baby steps. Python is really easy to get used to, so you don't have to be writing C to contribute to Puffer at all. Probably you'll want to write in like Python or something, because Python itself is slow. But if you haven't used Python before, it's literally you just write Python, add some types, and boom, now it runs 100 times faster. It's that easy. And the C is nowhere near as bad as it looks if you're not used to that. But that's not required. $28. LSTM works. Would you be open to an AEC implementation PR? Of course, but I don't know if you know how... I don't know if you know what you're getting yourself into there, is the thing. The reason that AEC is hard is because, well, think about it, right? Like, you're getting observations from different agents at different time steps. So, like, if you're going to use an LSTM policy, or even just for generalized advantage estimation and such, you need to keep track of which agent comes from which environment. AEC is this, it's basically turn-based. It's like Petting Zoo's name for turn-based environments. So I've been thinking about that quite a bit, Cole. And the solution that I have in Pufferlib is quite good, I think. It's going to be a lot faster and a lot less error prone than, unless you have a really good idea in mind for it. Let me explain how Pufferlib does this real quick. I heard turn-based. Yeah. So Nathan, this is relevant for you as well for your like Dofus environment. God, can I find? Okay, here. So this is why turn-based is hard, right? So normally when you get an environment, right, you have like agent 1, agent 2, ... right? And then this is going to give you obs. And then these are going to go into your model, right? Which is like, I don't know, some conv or whatever. And this one goes in, this one goes in. But then also, you have an LSTM state, right? and you need to grab like the state variables, right? S1, S2, and these need to go into here as well. Um, Even if you don't have an LSTM, you still need to keep track of which obs comes from which agent, because then what's going to happen is you're going to save this into a buffer, right? So you have like A1, and you have like O1, O2, O3, and then you're going to do generalized advantage estimation over this, which is very important. But like if you're going to take away one of these at a time, then what happens? Well, now you mess up all your indexing and you mess up your ability to like pack batches of data. So what Puffer does for this is we have a mask variable. This is already integrated with our default training implementation. What we do is we give you the option to return like a mask. And then what happens when you do that is this observation just never gets into the buffer. So we actually have buffers that support this. But you still need to have like this mask, essentially, which is a little bit inefficient. But there's not really a clear way to do this otherwise, at least without massively degrading the performance of vectorization. So I hope that gives you a rough answer, Cole. Like you can already do it in Puffer, and it's probably going to be way faster than anything else out there, just if you use this mask variable, and the algorithm will be correct. I mean, if you just want to look at like our vectorization, just to show you what a massive difference that we have in performance, and this is dated, it's even faster now. You know, we take Atari up from 4.8K to 25K, ProcGen from 40K to 150. The really fast environments go from 100K to millions, right? Even for environments where like they're pretty slow and it's really easy to make them fast. It's really hard to make them any faster. Like we go from 5 to 7.2, right? We can run environments like Neural MMO that just Gymnasium will straight up fail on for multi-agent. We've got like NetHack over 10x faster, Minigrid 4x faster. So the perf is there. Mm-hmm. Yeah, Splinter, check the link, the snake link. And for reference, on my way to Iceberg, see ya. Thanks. Hmm. And for reference, up until a few days ago, this like entire MOBA env was implemented in pure Python. So like this whole game was implemented in Python. Only reason I'm doing C now is so I can put it on the web. Python's plenty fast. Do you do masking for OpenSpiel M's? Yeah. So I think I only ever integrated Connect 4 with that because I had somebody that was trying to do Connect 4. But yeah, you would mask for that. That's how we were handling it for OpenSpiel. I actually don't know how fast the OpenSpiel M's are. They might already be faster, they might not. I'll see what I can come up with. Doesn't seem like anything implements turn-based. Because I've thought about it a lot, Cole, and the infrastructure for it is just like it doesn't make sense with vectorization because you would have to change the whole API. You'd essentially have to change the whole API, and like the way that we get our vectorization fast is by passing around like static chunks of memory. Um, And it's very difficult to do that when you have variable variable agent turns and stuff. So I don't think that there's a really good way of doing that any faster than we have it right now. Yeah. I mean, there are a couple relatively easy optimizations that I can potentially think of, but for the time being, we're probably like I would just use the Puffer version for now, and if you have a relatively simple environment, like Puffer will probably just auto solve it in less than a minute. This is not a problem of Nathan, this is not a problem of like there's no algorithmic problem here. It's just literally like you have to be careful with the way that you're storing agent observations and the like if they're going to come from variable sources. So somehow while answering all these questions, I think we actually got somewhere here because this is correct. So we now have an LSTM implemented in C. So that's cool. Right? Yeah. This is now correct. So let's look at how cool this is real quick. Let's just take a moment to appreciate how cool this is. From the top, I guess from right here, 21 down to 134. So like literally 100 lines of code for an LSTM, convolution, ReLU, sigmoid, tanh, linear layers in C. So literally it's 100 lines of code to just do all of this stuff. So now it's compatible with web and we can run it anywhere, right? We didn't need some crazy heavy framework. We didn't need to deal with like figuring out how to force Onyx to work in C. We didn't need to do any of that. It's 100 lines of C code. And we can probably make this shorter too. If anybody knows how to combine these two functions into one function without me having to put an if right here, let me know. Are you still in the academia space? Are you commercial now? I'm not in academia. Puffer's technically a startup. We just launched just a couple days ago officially. So this is a company, and we do offer support packages. So, if you're in academia, or if you know folks in academia who could benefit from having RL not be just a complete pain to work with and do anything, let me know. But all of our stuff is free and open source. We're pretty much just selling extended support and priority features and a couple extra services around that. And I will say that the progress in the last few months has been very, very rapid compared to academia here. It's been very, very rapid progress. So the one thing I'd really like to have here is I'd like to have a test in C somehow. I mean, not in C. I'd like to have like an automated test for this. I'm trying to think how we can do that though. Can you get detailed profiling like in Python? Yeah, I'm sure I can. I only asked because I watched your thesis defense. I wondered what your next thing was. Cool, Puffer is full-time. Nicely done. Thank you. Yeah. No, Puffer is... I think that this is going to change the whole field very, very quickly. I mean, when you can just run like tens of billions of steps worth of experiments per GPU per day, field is a whole different place, right? It's like I say in the iceberg video. If you haven't seen that one, I highly recommend that. It seems like YouTube has not picked up on this video yet, but at least I personally, I thought I did. I thought the delivery was way better than my thesis. We'll see if people agree with that, and if it just takes a little while to get into the algorithm. But, yeah, okay, be quiet, you. But yeah, I posted this a few days ago now. Has all my thoughts on RL in the field. All in one place. Let me figure out how we're going to write this test, because kind of what I want to get done today, what I want to get done today, I have the working LSTM, I have working linear layer, I have working comp layer, which is technically enough to build whatever I want. But these functions are kind of jank. I want to at least add like a little bit of structure to this, just a tiny bit. And I don't want to break them in the process. So I'd like to figure out how to have an automated test. It's just a little bit obnoxious because I'm technically relying on PyTorch and C code. I guess technically I can just write the outputs to a file, right? And just compare the two files. Clicked on your thesis video because I saw a game in the thumbnail. Yeah, fair enough. We talk about lots of like RL and game stuff in the Puffer video. It's a very good overview of like the field. Hey Tenny, welcome. We're working on some stuff here. I think what we're going to do is we're going to take the next little bit to build out some tests for this. What's that? What is? Problem with views is the iceberg is not normie friendly. No, the iceberg video is actually way more accessible than my thesis. Like the stuff in the iceberg video is actually like, I threaded it through with like higher level stuff that should be more accessible. Writing to two files and comparing. Yeah, it is kind of jank, but what else would you have me do, right? Like, I have to have, like, otherwise I have to bind this. I could write like a Python binding for this and then call it from Python, I guess. Right? Maybe that's better. I mean, how bad would that be? Let's say that I just take all these, I put these into like puffernet.c or whatever. I make like puffernet.pyx, I make a Python binding. I import that into a Python test file. That could work, right? Maybe we will just do that. That would be cleaner. And I wouldn't have to do like the write function in C. Yeah. You've convinced me. What the heck is this? Oh yeah, we don't need this. Puffernet.c. We don't need the MOBA. Load weights can go at the bottom, right? So we'll just clean this up. Whoops, not below the main file, but we're not going to even need a main function. And this is actually just going to be a .h, not a .c. What are you working on? Since we have some more people, I'll go over quickly. So right now, my main thing with Pufferlib for the next few weeks is ultra high performance simulation, just making lots of really good environments so that we can get experiments going in RL. Part of that is making it accessible so that people can actually see these environments and play around with them and see what's going on. So I have these running in the web. Like this is a MOBA that I wrote. We're going to get more environments into web soon. This is written at 100% in C, compiles to WebAssembly, runs at 1,000,000 steps per second. So it's very, very efficient to play around with this thing, and all different characters and whatever. It's a very efficient environment for research. It's a very efficient environment for testing out your RL methods, it's great. But in order to actually have these guys do something and not just have me controlling them, right, I want to have my RL bots actually control them so that you can watch what the RL agents do and you can play around against the RL agents and stuff like that. And generally, that's just a really useful route to go. And it's not that hard. All I have to do is make a few of the PyTorch layers work in C, and then I can compile them to WebAssembly, and then we can run them in browser. So that's what I'm doing now. That might sound kind of crazy, but it's only like 100 lines of C. For linear, LSTM, convolution, it's already done. Now all I have to do is make sure I don't break this stuff, because it's very easy to break it. Write a couple quick tests. I've already manually tested it, but I need to have like an automatic test so that when I go to refactor this a little bit in an hour or so, as soon as I finish that, I don't break it by mistake. Because like right now, I've done all of this stuff with just like raw pointers, and it works, but you have to be very, very careful about like, you know, making sure that you compute the offset in memory to your bias term correctly and things like that. And some of this I can just make a lot easier. So I want to do that refactor, but not until I have a quality test. So yeah. You could equally fast if factor is const. I don't know if that quite works because we need to use both of these functions, Stein. But actually, just reading your thing, I got an idea as to how we can do this with one function up here. So you've jogged my memory, so thanks for that. Do you think RL is superior to evolutionary strategies? If we're speaking generally, then yes, because the problem with ES is that it bets against hardware. Like the classic implementation of ES doesn't really benefit from GPU. It really is like a CPU type implementation. It's a really bad idea to bet against advances in hardware. It's also like you're not actually getting a good gradient signal. You need a ton of samples to approximate gradients. So it's very difficult to scale that stuff. And we haven't seen anything crazy come out of ES yet. Yeah, I haven't really seen any super crazy results come out of ES. There was some cool stuff from like Ken and Jeff's Uber group several years back, but I haven't seen anything since then. Let's get puffernet.c written real quick. Holy viewers. Welcome, everybody. I promise we're going to actually, like, buckle in and, like, write these tests in a second so we can get some more stuff happening. But I will just one last time, since we're so close to hitting this milestone. Like, 15 stars to go until 1,000 on Puffer. So, you want to make that happen, help me out, guys. Okay, so we don't really need any of this stuff in here, right? All this stuff is just jank. At least we don't need this stuff. We'll consider whether we need the rest of this test to be here, or we're going to put this portion of the test in Python. Get out. What's this? We don't use this. So LSTM, conv, sigmoid, relu, linear. Okay, so this is good. Puffernet.c, puffernet.h. Now we need to make a puffernet Python file, right? In order to make a Python binding. Hello, this is Amos. Welcome. We're writing some CNETs. I'm going to want just the prototypes of all these functions, right? which is if I actually wrote a proper .h file, you know, but we don't really do that much. Maybe I should consider doing it, I don't know. The only thing that's making me tempted to write proper .h files is that, you know, H and C instead of just all H, is that you end up needing the prototypes for Python anyways. Though I think then you would still need it. You'd need another set of them. Only 14 to go to 1K. Thank you for your support. It helps a ton. It really helps a ton. Factor should be an argument to function. I'm gonna head out. Till next week. See you around. Thanks for dropping by. I already grabbed this one. So we just need the LSTM, right? Yeah, look at that mess of a signature. Okay, so these are our functions, and I need to go just grab a little bit of, what is it, SciMoba? Yeah, so I just want to grab this just boilerplate. So we have all these flags on. Oop, profile should be false. And we don't really, do we need any of this stuff? I think we do need the NumPy APIs. We're not going to need all the other stuff. I think I need all of the function prototypes, right? So we'll do... I can literally just copy these in, can't I? Like this. This work? And then if I can get a binding for this going... Hold on, I'm trying to remember how I did this in the Python version here. So I defined all these types, right? And then how did I bind them? Knit. Yeah, I need this logic here to remind me how to do the casts from Python side. I think that what you do is we're gonna end up with name conflicts, right? Well, I think this does it. Yeah. You just need like these wrapper type things, right? And then right here, you need to cast, I think. I think you need explicit cast on stuff. And they're formatted a little weird. So it's like float star, input data, float star, weight data, float star. This cast syntax is weird in Python. But the alternative binds that I found for C, like I think Python is generally the easiest for numerical computing. At least I haven't found anything that I like more than Python so far. We'll clean up the syntax for this in a bit. But yeah, I think now this should autocomplete, right? Yeah, this will just autocomplete. Let me make sure that this didn't mess anything up. Looks fine. Okay. So now we have a 50-line Python binding for puffernet. And now what we do is we make a Python file called test puffernet, right? Oops. And we don't need this. I want to figure out, there's a Python line to like one line pix import or whatever. I guess for now we'll just do from pufferlib environment oceans moba import puffernet puffernet, and then yeah, def test puffernet linear layer. We'll just make some like batch size is 16, hidden size, input size, right? So test linear layer. And then we'll just do data. A range. Min space. Something like this. I don't know if it needs to be reshaped. I'll pull this up on the side. Puffernet.c. Oops. .h, I guess. Okay. So we have linear layer. And now we need to do p. Make dummy data. Weights. And this needs to take args, right? So inputs numpy is going to be input size. Weights np is going to be input size times hidden size, and then output np puts equals zeros, batch size times hidden size, right? Text type numpy float 32. Okay, so now we have this data, right? And we do puffernet linear layer. And now we have to do the torch data. Torch. It's going to be this. And then we do want separate zero function like this. And then we just do torch linear equal torch.nn.linear. We don't need this output because torch is not in place. We do like this, right? And then what we have to do is we need to have like an assert all near, like so assert near a b. Oh, I think you can just do this, right? Yeah, but let's do it this way so that we can have the shapes match. Imp numpy. No, we'll just do both numpy, right? Yeah. Assert near a b. So assert a.shape is b.shape, and then assert numpy all less than 1e minus 6. Okay, and now we'll do assert near numpy. Perfect. So this is the basic form of our tests, right? Is that we have some dummy data, and then we have the same dummy data, and we want to make sure that our two things match. Test puffernet linear. Puffernet.pyx, right? Does this compile? Yeah. I see your error, Bet. Let me fix that real quick. What happened here? Expected 0 got 11. What the heck? Do we use this file? We do, right? This is our main binding. Well, this definitely takes some args. MOBA star. Expected 0 args. Yeah, that's really weird. This was working before. Oh, I think I know. Yeah, I think I know. So let's just change. I think that we just forgot to change this. No? Okay, we're gonna comment this for now, but I will fix this today, Bet. You can yell at me if I don't. I think that we're defining the same thing multiple. I think that it's because I have multiple different Python things. I need to fully port from the old version to the new version is all. So let's see. What do we have here? Puffernet.h. Apparently we use a couple depths. Dude. Was it? Do we need standard IO? I think we need standard bool. Why can't I type? We need math as well. MOBA start init MOBA and puffer tank has empty parentheses. I don't know Python. Oh. I think you're right. Hold on. Ah. Yeah, you're right here. Thank you. I forgot because I was just adding like a prototype or something. So I forgot that I actually had to, yeah. It's one really obnoxious thing about Python is that you have to give it the whole signature for everything, even though it's already defined in C. I don't know why, but it's really obnoxious. So, like, the fact that Python essentially makes you do header files anyways makes it really, really redundant to have to split your code into headers and the source C as well. Thanks for the fix. Comparison of... We don't need this, right? Agents. We don't need any of this crap in puffernet. We have one warning here. Different signedness. Weights. Good by me. What are the craziest RL simulations you've seen? Well, it depends what you mean. Like, they didn't rewrite Dota for RL or anything for OpenAI 5, right? Like, it's the craziest use of RL I've ever seen. And in fact, in my video, I say that I consider Dota to be the top result ever in all of RL. But as for like people who've coded up some crazy simulations, I think I'm at least in the top 5 there with the stuff that I've done. The other one I know is CraftX is a crazy project. That's a crazy project. Madrona is a really cool thing. It's like an engine for GPU simulation. I don't know if I like it generally, but it definitely has some really cool uses. Yeah. Some stuff like that. Test puffernet. Simulation of plasma infusion reactors. Ah, yeah, that was in my video as well. That one's pretty darn cool. See, that's the type of thing that I would love to help out with Puffer, right? I'd just like to provide people infrastructure in order to solve all the cool industry problems with RL. Hey, we do have support contracts now. Support packages, really, more than contracts. That is newly launched. Seven arguments forgiven. Okay. What do we need here? We need input weights, bias, output, batch size, input size, hidden size, like this, I believe. Must be matrix got 1D tensor, okay. Dot. Invalid input for size 128. Question mark. Oh. Input NP. Batch size, right? Got 1D tensor. Input torch. Okay, that looks good. Mat 2 must be matrix, got 1D tensor. Oh, you didn't reshape the weights. Yeah, I forgot about this. I'm actually wondering, like, can't I just reshape these? Can I just do like this? And then I can just make this in the shape that I want it. It's still contiguous data, right? WASM. And then I don't have to do this view bullshit here. Probably don't need this float either. We want it already to be in float 32, right? Cannot interpret 128 as data type. Right. Okay. Still cannot be multiplied. Well, they're the right shapes now, at least. The weights get transposed or something, don't they? Hold on, do the weights have to get transposed? Yes. Alright, let's see what's wrong. This looks... Oh, totally wrong. Whoops. Yeah, there we go. Output NP, output. This is... Whoops. Upper. Cool. So, assert near, output, upper. And we also need to know... because I see some of these don't look quite correct. Let's just do this breakpoint here. These are good. But these are totally different. So we'll have to figure out what's going on here. Because we tested that these are correct, so now we know it's that the test is wrong. Right? We know it's the test is wrong, not the code is wrong. Let's see, uppernet.h. Linear layer, input, weights, bias, output, batch size, input dim, output dim. Right? Okay, well, we don't know about the weights yet. It could be that the weights need to be transposed, right? Let's see what the weight dimensions are. Oh, well, it's 128, obviously. Still doing the Dota RL and C. Yep. In fact, we're doing something that is going to benefit both that project and a ton of others at the moment. I'm writing a very small inference library in C for just all sorts of different types of neural nets that we're going to use. So we have comms, linear layers, LSTMs, and a few activations so far. I'm writing the test for those right now, and the hope is that what we're going to be able to do is we're going to be able to upgrade our agents on the web. So like these guys here, we're going to be able to give all of our different AIs some like really nice policies, and they're going to run on the web, and it's going to be very easy to play around with them. It's going to be very easy for people to like see whether they're good, like give feedback and stuff. So we're going to just finish all this up right now because it turned out to not be anywhere near as hard as you would have thought. It's basically like 100 lines of code in C for LSTM, convolution, and linear layer. Right in the test, though. Let's modify this so that we can at least see if we have the shapes right. Another cool example are bots in Rocket League. Yeah, I've seen that. That's also pretty cool. Ugh. 64 by 128. It's backwards. This needs to be transposed. I don't know why, but apparently they do transpose weights. Cannot call attach. Attach. Okay. Output puffer. Output torch. Still completely different. Still completely different. And we know that the implementation is correct as well. Yeah. I'm trying to think what else it could be. Well, hold on. Why don't we do this? Let's see what this looks like. Possible that I only have it correct for square layers. I would doubt that, but it's possible. Okay. Torch.matmul weights torch input torch. Shape 16 by 128 plus bias torch. What is it? Torch bias torch. Torch. 3. Yeah, so this is consistent here, right? With the linear layer. Their linear layer is consistent with this. So this is the right. Input weights bias output. Okay, where else could I have messed this up? Is it possible that, like, by reshaping this data, it's, like, not contiguous or something? Contiguous. Is there no, like, dot contiguous? Reshape in torch is weird. It shouldn't be. Yeah, no, so this is still way off. Trying to think what it would be. It could be the binding is off. Hold on. Puffernet.pyx. So here we do puffer linear, right? Input weights, bias, output, batch size, input, output. Input weights, bias, output, batch size, input, output. This all look good to me. TensorFlow over Torch is a very weird take. But generally, people like PyTorch way more than TensorFlow. Well, to be fair, Torch becomes very bad very quickly once you go into the internals, but at a high level, it's very nice. That said, TensorFlow is equally horrible with the internals, if not worse, so... I'm trying to think what this would be. Batch size times input size. Input weights. Hold on here. No, because I did make sure to zero the output, right? Yeah, the output is zeroed. Do I need to transpose the weights that go into, do I need to transpose the weights that go into puffer as well? Would that do it? That could do it, right? Using tensor. And I did that way back in the day and it was not fun. Maybe the matmul. The thing is I've tested the matmul independently. So it's possible, but I would consider it very unlikely. I think it's more likely that I'm putting the data in wrong. Let's just do hidden size, input size like this, right? What if I do this? How big should I expect the outputs from this thing to be? It's also very concerning here that a lot of the entries in the puffer output are 0, right? Matmul. Yeah, I did that already. It matches. The torch implementation matches. It is definitely an issue with the way the data is getting loaded, but the question is what? The question is like what issue? I think this is probably closer because this should be closer though, because now I'm not having to transpose anymore. And this should be the order in which the data is written out to disk, which is how I tested the linear layer. Dummy inputs. Input numpy. Weights numpy. Puffer. Let's just do a quick little test to make sure that I'm not totally wrong about the puffer layer being correct. One, one, two, two. Four. It's gonna be 2, 3, 4. Type bias. Output buffer is gonna be 4, and then hidden size is 2. Buffer net. Hold on. Let me do one thing real quick. Be right back. Okay. Is the repo open for contributions? Yes. It is all, this is all open source. It is at Puffer AI, Pufferlib right here. Store the repo on your way in. We're almost at 1,000. Helps us out a lot. Nice. 14 to go. So it's 4, 2, and 2. Let's see if I'm wrong about this being correct here. Yeesh. Well, that's not good. Yeah, that makes no sense. It could be an issue with the binding, though. Could be the pointer's not getting passed correctly. Could it be site? Yes, it could be. That's what I'm trying to figure out. Any issue when data is getting converted from NumPy to Torch? Well, here right now we're doing NumPy only, and the data is clearly wrong. Yeah, you tested in C and it's seen fine. Yeah, exactly. So there's something weird about how the data is getting passed, I think. Because if we look, right, this data is reasonable. Hidden. Put dim output. Yeah. So something is definitely weird with how the data is getting passed. I'm trying to think what that would be. The types are all. Hold on. Is it this? Ha. Gotcha. Gotcha. Does anybody want to guess why this happened before I explain? That's evil. That is evil. Holy. Was it 16-bit? Close. 64-bit. Wrong bit precision. Hot damn. Absolutely evil. Goddamn bits, yeah. I was like, what the heck? Am I dumb? Did I test it wrong? No, you just put the wrong data into it. uh, output puffer. Ah, now all our data is populated. Look at that. I think 1e minus 6 is a little bit ambitious. 1e minus 4? Yeah, there you go. So we match to 1e minus 4 on the outputs of a linear layer. That's perfect. I'm going to take this out of here just so we don't have it, but I'll save this just in case we need it down there. So all we do here is we write the convolution, LSTM, and the activation tests, which should be quite easy. And then we will clean up the puffer net. It's 3:25 p.m. So I think we should be able to get all that done today and probably even get these onto the web. That might be a little ambitious, but at the least we'll try to start building some real networks today with this. TBH, first time I'm enjoying my 4 a.m. noodles and coffee breakfast. Jeez. That's rough. I spent many years in college, like, dinner would be like the fourth Monster Energy of the day and ramen or whatever next to the lava lamp and like the super try-hard Arch desktop in college. uh, I was like giga cringe. Can you explain why it's not able to assert 1e minus 6 precision? It's Frankly, I don't know. There's probably just a difference in the compilation settings. Like, I don't know, maybe Torch is compiled with, like, fast math or something on. We'll have to mess around with the compilation settings and see if we can figure out what Torch uses. Because it should really be the same. Like, it should literally be the same operations. But, you know, there are different compilation settings that could screw with stuff. They could be doing some weird things. I don't know. It's to within 1e minus 4 in the outputs, which is pretty decent. We should look at that, though. Because, yeah, technically, even if this is, like, even if ours is correct and theirs is correct, we do want to match them pretty closely. I also think that we probably don't want to have constants hard-coded up here. Out of my element here, just enough to really show. You'd be surprised how quickly you can pick this up. I haven't programmed in C for 10 years. I'd only really briefly used it in undergrad a little bit, and I've been doing this for the last week and a half. No, not even. Like, the last week, pretty much. So, yeah, it's not that hard. I mean, of course, like, you gotta keep in mind I've done this type of work for the last 10 years as well, so I kind of know... I know all of the possible errors already. So that helps. But hey, if you're trying to do like some lower level stuff and get into RL, make some cool environments, right? We can always use we could always use some contributions. If I've got to learn something new either way, why Python over Mojo? Mojo is a random new language designed by a company that I don't know what's happening to, right? Python is an extension language that's just an intermediate layer between Python and C that transpiles directly to C and is also a gateway for you, you know, going from Python to Python to C directly. It's like a bridge layer anyways. So that's why. Also, some of the stuff that Mojo gives you is just like, it has like weird Rust inspiration that's completely irrelevant. I do like they've got like some SIMD support and stuff that's kind of nice, but I'm not I'm not using some company's random language that's like, for all I know, company will be bankrupt next year, right? Okay. Upper net. So you can see here, like, I could have written all of this code in Python. Like, I could have written all the C code in Python here, and it would look almost the same. It would just be, like, slightly more Python-y syntax, and it would be just as fast. I pushed it one layer deeper into C so that I can use it independently in C and compile it for web. But you see how it's like you're not even really learning something new with Python? It's just like an intermediate between two things that you should know anyways. Okay, we have batch size, input size, hidden size. In width. channels, out channels, kernel size, stride. And let me find how I did this test in C. Because I believe I have this somewhere here. Yeah. So now what we're going to do is Python probably uses double floating point in its math. C port using 32. No, PyTorch should not be using double precision in its math. PyTorch is using float 32. I think it's compilation settings. I think it's like the thing is their settings like you can compile with like dash at like dash fast math or whatever. Yeah. I don't know, like, they're probably just some different compilation settings or something. There could be really any number of things. It could be like the order in which you're adding the numbers. It could literally be that, right? Like loop order will matter. I can also basically guarantee you that, like, here, the order that you add the numbers matters. And PyTorch is almost certainly doing like a tiled matmul instead of a standard matmul, right? So that's going to be different. That's going to change the order. There are lots of optimizations here. Like the puffer one right now is just a very boring, simple C implementation with zero optimization so far. We might end up optimizing it a little bit. We're not going to try to ever make it as fast as PyTorch. It's just for like testing and inference in the web. But yeah, that's like that gives you a little bit of an idea. Not a bad guess though. Weights. Whoops. Okay, and then we do input torch. And now what we do is we see whether this thing actually did something reasonable, because I suspect it didn't. Usually LLM slop. That's why I don't autocomplete sections that large usually. We forgot to run it. The cool thing about this is we can also do like a perf test with this. So we can see like how slow ours is compared to Torch, and we could actually like build this out if we wanted to. Okay, so okay, we got our weights the same. This actually looks good. Maybe we got the output shape wrong. Output for shape. Right, so the output is totally the wrong shape. So we have to do there's a formula. Yeah, this formula right here. So we'll do out height, in height minus kernel. That should be good. Torch. Buffer. Okay, so let's see what's wrong. Well, first of all, these values are massive. I think we're going to want to adjust our data function. Two pi. Let me see if we can just get ourselves some better conditioned data. Okay, you can't do like that. Yeah, so this does float. Let's do like this. Okay, so this actually works now. We just had to get our data to be better conditioned. So floating point precision, right, is most accurate with like small values around 0. So when we have massive numbers, because like the comms keep accumulating more data, right? So we were getting numbers in the thousands. Like you're not going to be able to have 1e minus 4 when they're like thousands. You get like 4 significant figures, not 0.0001 worth of accuracy. Right? You get 4 significant figures maybe. Python standard float. But this shouldn't be Python standard float because this is PyTorch and the PyTorch is calling into C++, right? Which is then calling into cuDNN or, you know, whatever the CPU implementation is. So there's kind of a big stack there. Hence why I said it's like potentially more complicated, right? Tab, 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 tab. So the reason I'm tabbing all this is because I actually have the same test down here already. So just should need to refactor a little as well. We'll see if it instantly works, but I doubt it. Maybe Super Maven's goated. Yep. There you go. Issue. How often do you stream? Usually Monday through Friday. Sometimes I'm doing other stuff. Like yesterday, I had a co-working thing, so I was only on for a short stream in the evening. But I'm usually just like streaming my work, you know, when I'm working. Except Saturday, I take off to just do solo dev all day. Like Saturday, for instance, last Saturday, I ported the entire MOBA to C in like just 8 hours of just frantic coding. At least the initial pass of it. So like stuff like that, occasionally I'll just do off stream. But I stream most of my work. I also, Punit, I don't think that's correct. I don't think it's 32 decimal digits of precision. It's Python's 15 decimal digits maybe is like the best it could represent, but you don't get all the values there. And then for C, it's 32 bits, which should be the same. Possibly there's some difference, but I would doubt it. Puffernet.h. Okay, LSTM. Input weights. Yeesh. What happened here? Weights, input. How did it even mess it up this bad? Like, I literally have the correct code down here, don't I? Yeah, you need state. What the hell is it doing? Whoops. In here, right? Input state H, P, and then we have weights input, weight state, bias input, bias state. We also need buffer numpy. You need a buffer, which is this size. And then you need batch size, input size, hidden size. Okay. So, and then the signature here is input state H, state C, numpy. Then we have weight state, weight input, weight state, bias input, bias state, buffer, buffer. Unfortunately, funny story, I tried to get the PyPy package named Puffer, and I couldn't because there's a Python buffer that somebody named Puffer. So if anybody wants to get me that package name. But I think that's actually something that gets used. Did I still mess this up? I think I counted wrong, right? Or maybe the binding is wrong? What's the origin of the name? Almost get killed by a puffer? No, man, puffers are friendly. It's literally as simple as just like, hey, I'm writing like infrastructure and middleware. I have no visual depiction of my work for you whatsoever. So screw it. We're gonna have a fun mascot. Here, have a pufferfish. It's very memeable. Like, look at this guy. He's very memeable, right up there. I don't know. More companies should have mascots. They're funny. Yeah, he's nice. I mean, pufferfish are not gonna kill you either unless you try to eat them. Like, they're not going to poison you if you like by biting you. It's just if you try to eat them. Though the bigger ones will take your finger off if you wave it too close to them. But if you piss me off, I'll do that too. I will take your finger off. Yeah, but so am I. uh, buffer. You don't need this output buffer variable. That's what it was. Yeah. Now we do actually have to make a little change here though, because buffer will mess with the data. So we have to do state H torch, state C, bias, and then what we do here is output torch, state H torch, state C torch, okay, and then glad I dropped by. Be back in future. Thanks for dropping by. Cheers. Come on. Not enough values to unpack. Shape error. Let's see what's wrong. Ah, that's weird, right? That's real weird. So close to having this done. The activation functions are going to be super easy to test. And then we'll basically be able to just refactor however we want very nicely. We can perf optimize, whatever. We can build some networks. We can put it on the web. We can literally do everything once we have this test. And I like the way that I did this as well, where like I manually tested in order to make sure that it was correct, right? Like I just did a bunch of interactive testing, and then I wrote the formal test in order to allow me to refactor the known good code. And the reason I did that is because just like a test like this wouldn't even help me before I had it correct, because I need to check like at every stage of the operations, right? Just having like binary yes no isn't correct, isn't helpful from this. At least not earlier. So why is the H state like this? I think it's because you need to have this like extra obnoxious layer variable, right? Well, first of all, this needs state dot view one batch size hidden size dot view. This maybe? This is obnoxious. For unbatched input, how did I test this before? 1 batch size minus 1. State 1 batch size minus 1. Okay. Insertion error. H numpy. H torch. Those look the same to me. Those look the same to me. H torch. Ah, you gotta strip the you gotta do this. Well then. Oh well then. Ho hum. That feels good. Puffernet.c. Definitely cleaner than comparing two files. Yeah, that was kind of a dumb idea. But to be fair, like, it does mean that I have to have this annoying Python binding, which isn't bad, I guess. I don't know. I'm really surprised that nobody's done this. Like, why the hell doesn't this already exist? Like, it's not that crazy of a project, right? To just, like, write a little neural net library in C, and then, like, add some Python bindings. Not that hard. Mm-hmm. And Testarello. What do we think? This isn't in place. Oops. What do we think? Assertion error? Really? Oh, really? I'll put puffer. Ah, because it's... Here we go. Now we do test puffernet sigmoid. I think this is the last one. Probably literally will autocomplete for us because it's like, this code is very samey. Man, that is crazy that it's still... Well, it takes one argument. Oh. Shit. Okay. Yeah, I forgot that I did this as a, huh. Well, input. I did this for a single element, so I want to just have a nice test like this. Really? Oh, -4. Try this. Okay, there we go. Here are all of our tests. So now we can get rid of the rest of this stuff, right? Now we can get rid of the rest of this. Still need an epsilon tolerance, yeah. You fixed now, my comments have latency. Ha. It's good. I tend to like program very reactively. So like I won't bother to like think in order to prevent a bunch of bugs. What I'll do is I'll just get my dev loop to be really, really fast. And then it'll be like, see a bug, think about bug, fix bug. See a bug, think about bug, fix bug. Instead of like trying to fix 5 bugs at the same time or trying to anticipate stuff. I don't know. Maybe that just makes me really brain dead, but it's very effective. And now you guys can have this in dev as well. I'm going to use the restroom real quick, and then I'm going to be back in a couple minutes. And what we will get to do is we'll actually get to take these things. We're going to refactor the C API just a little bit, and then we're going to start putting together some actual real, like, good neural net architectures and trying to load pre-trained models into them. Like, we're going to have, like, conv, MLP, LSTM type architectures. And then that'll let us like have that run on web. So I'll be right back and then we'll get doing that. Okay. Presenting puffernet.c. This is so cool that this was like this quick to build. I think what we're gonna do now is we'll just go into. I'm gonna grab one other thing real quick, and then I have an idea. Well, I know what we're gonna do. So, I don't want to introduce too much overhead into this stuff, right? Like, I don't know if I want to have like a general tensor class or anything like that. I don't think I want to get that much. I don't want to get into it that much, but potentially just having. Hmm. I'm trying to think if I want structs for the layers actually. Let me think about that. Well, we can definitely remove this linear layer accumulate if I'm a little clever. It's stuff like this H out, this W out, right? Like technically I could do like struct conv2d, and you would initialize it with like batch size, in width, in height. You'd initialize it with all this stuff, right? And then the conv channel would be, the conv layer would be easier maybe. Do I like that? Well, yeah, I think I do, because otherwise when I'm building networks, I need to have the pointers to everything. Which brand is this committed? I'll show you, right? I'll link it to you. Remember to star the puffer. Helps out a ton. I'll link you the file. So the test is just in the base right here. And then it's in pufferlib, environments. It's going to get moved into like, a more general thing. But for now it's in here. MOBA, where is it? Puffer net dot. Huh? Where is this? It should be in here. Puffernet.h. I mean, I committed it, right? Okay, there it is. I don't really understand why you need these relatively small operations to implement an RL model on the Where do these math layers or steps reside in a full So, because I don't need to train on the web, right? I just need to like load. I have all of Pufferlib for training, right? All I need is I need to be able to load the weights of a PyTorch model into a C model that behaves exactly the same way, and then I can run that on the web. That's all I need. And you can see, like, let me give you an example. So this snake game here, this is RL agents running in your browser. But this is just like, if you saw I already had like an MLP implemented, I already had the linear layer implemented. So I can only make these like an MLP, which is not a really great architecture. So by adding the LSTM and the conv layers, I can implement way stronger models, which are going to be needed for, honestly, even the snakes would be better with that, but definitely for the MOBA. Yeah. Yeah, there's no reason to train on the web, right? That's just dumb. I mean, you could kind of do an interactive thing if you really wanted to, but like, way more effort than it's worth. This is not that bad, right? Like, look at this. This is, frankly, and we're going to get rid of this main as well. So 130 lines of code. We're going to actually, there are a few other things we can clean up. This will end up being a total of like 150 max. I think that that's a win. I think that's a huge win. Okay. So let's do type def struct. Do I want a type def struct? Hold on. MOBA type def struct. I think you do struct linear, and then you do type def. What's it? No, it's type def struct linear, and then you need to do. There's like a weird Python thing. I think we have to do it this way. Struct linear. And then when you do your linear layer, right now you have weights, bias, input dim, output dim. You still need to know your batch size. Do I want to have a tensor class? Or a tensor struct, I mean? I'm trying to think how silly I want this to be. Okay, this is important. So, I have to pass batch size explicitly. If, If I just pass a tensor, then the tensor will have all the dimensions I need, right? It's so funny how you see, like, basically as soon as you go to introduce any amount of abstraction, you just realize that there's a cost immediately, right? Well, this is at least this is very free. So let's do this first, and let's see if I like it. This is like pretty easy for me to stomach here. Because now all I need to do is linear layer of struct, where is it? Linear layer. Linear layer float input. And then you don't need any of this. All you need is the batch size. And then this is a linear star layer. Linear input dim like this. Or you can just do int input dim is int layer input dim, then int output dim. Weights. Is this better though? Doing this way, you should always be able to create a tensor and wrapping in future without having to do all of your flattening work at the moment. Well, yeah, no, I'm fine. Like, I don't have to redo any of the crazy work. It's just a question of what I want the code to look like. So, like, every time you introduce a piece of abstraction, it's never free. There's a cost, right? So, like, I can add this linear layer operation or this linear layer struct here. And if I do that, then I get to have the weights and the input dims taken care of. So I don't have to keep around wherever I'm calling this. I don't have to have a ton of different variables to represent, you know, to make sure I know where the weights and stuff are for this. But the cost is now I have to, you know, get these variables from the struct. And now I have, you know, these pointer ops here cluttering the code where it's not quite as easy as before. And I mean, you can go really crazy with this, right? Like, I could decide that the weights are a tensor, the bias is a tensor, like it's done in PyTorch, and then the input is a tensor. So now everything's a freaking tensor, and now, like, this thing is suddenly going to blow up and be 30 lines of code for a linear layer. So let me think about that. Well, here's another question. Do I actually need the batch size to be... No, I do want the batch size to be part of it. Otherwise, I end up with a whole bunch of additional functions. Welcome. Making a few decisions about how I want this to look. So essentially, let me just like walk through my my reasoning process right now. So I have this very nice and simple pure C library, right? It's got conv layers, it has LSTMs, it's got all this stuff. But if you look at the function signatures, you have to pass everything to these functions. So like when I go to implement an actual neural net, right? Think about how I would have to do that right now. I'd have to make like a giant struct that's going to contain like, you know, linear layer 1 in like linear layer 1 weight, linear layer 2 bias. No, conv layer 1 weight, conv layer 1 bias. Whereas if I introduce some layer types at the very least, then all I have to do is allocate these in the all I have to do is allocate like a much smaller number of layers. Is it hard to create in C? Nope, not at all. This was actually very comfortable. This was a total of like 2 days of work. And I have not written C in 10 years. You've been lied to. C is actually very comfortable and very easy. Frankly, stuff like this, figuring stuff like this out annoys me a lot more than just writing basic functions. The design portion is the obnoxious bit, because you're always wrong. No matter what you do, you're always wrong. Oh wait, I think I've got a genius idea. Hold on. Yo guys, I think I figured it out. You always hate it a year later. Is it Cython? No, this is C. We also have Cython around. And for contributors to Pufferlib, you're perfectly welcome to write stuff in Cython. It'll be just as fast. The reason I'm doing this in pure C is because this is going to run on the web. That's why I'm writing this right now. I'm going to put this on the web, and you're going to be able to play games with and against reinforcement learned agents that are just running in pure C. Which is pretty cool. So here's what I want to do. I think that we're going to be a little smarter about this. So we keep the struct, okay? And we'll rename this stuff in a bit. But like, what about void? Let's say like linear layer from struct, and then we do int batch size, and then what we do, we autocomplete that. What do we think about something like that? So we keep our very nice C functions, right? But then in order to maintain all the data that we need for the layers, we have a struct, and then we have something that calls the method on this with the struct. What do we think about this? And then if I inlined this, it would be the exact same code, so there wouldn't even be any overhead. I think it's nice. I still don't like the batch size. It will be available on your YouTube. Well, I'm streaming, like, the streams are available on YouTube. The VODs are all on my YouTube. They're like, I don't know, probably 100 plus hours of VODs on my YouTube at this point. Occasionally they get broken up by internet outages, but if you just, like, click through them, you'll see all of them there. The code is free. It's free and open source. Like, here, you can play around with it right here, and I'm updating it live. Well, frequently, not directly live. But yeah, this is all stuff that we've built today and yesterday. What do we think about this? The batch size is a little awkward, isn't it? So technically I could remove the batch size portion from this, and I could do the batch size as an external loop, but I don't know if I want to do that. I think that there are optimizations. Yeah. I don't think I want to do that. Let me just really quick, because I forget, let me just GPD. There are any common optimizations for cons that involve pushing specifically the batch loop batch size from the outermost to batch size outermost into an inner loop. Yeah, that's what I thought. So I think we want to keep the batch size loop here because there are optimizations we might want to do that will involve pushing this loop into the middle. How optimized does this have to be? For now, it doesn't have to be very optimized at all. But, like, I don't want to do stuff specifically that's going to gimp our ability to make improvements to it, right? So, like, if I were to take this batch loop out of this function, then I wouldn't be able to push it. Like, right now, I can just move this down lower, right? And the code will still work. And that can improve cache locality and such, depending on how we optimize. This batch size parameter is going to bother me. I guess the only reason that this batch size parameter is here, right, is because we don't have an input tensor. I'm fine having the output tensor be separate. In fact, I could make the output part of the linear layer, right? That wouldn't be bad. Can you explain functions for 1 minute? Yeah. So I'm implementing here. This is a linear layer. This is like your nn.linear in PyTorch. I've got ReLUs and sigmoids. I've got a convolution layer. I've got long short-term memory. So I've got common neural net layers here, except that they're implemented in pure C. I have a test for these that ensures that these functions exactly match the PyTorch implementations. So if you run in PyTorch, if you write like nn.linear, nn.conv, whatever, they work exactly the same way as my functions do. which means that I can load the weights from a PyTorch model into this, and I can replicate the functionality exactly. Now all I'm doing is I'm trying to clean this up a little bit because we're going to have to use this to build some actual neural nets. And like right now, you see how many args these functions take, right? Like I have tons of different pointers to different weights and things that I'll have to keep around. But you can see how simple this is. Like, okay, like don't even look at the stuff at the bottom. That's outdated. That's a load function. So 130 lines of code for basically all the stuff that you will need for lots of different types of neural nets. 130 lines of C. It'll probably be 150 lines once I add some structs, but still. Uh, uh. I guess the one other thing that would be really nice is, well, no, it really doesn't help us to have like a tensor class at all, does it? Tensor class literally just gives us batch size. Can anybody else see like an easy way to like have batch size be somewhere? Like linear layer shouldn't take batch size, right? Input shouldn't take batch size. You'd have to make a tensor class, is what I think. Or tensor struct, I mean. And like, is there really a point of doing that? I think that's too much abstraction. I don't mind this linear layer because it just lets us group some data together. And like realistically, right, when we implement this, the names are going to be like this. It's going to be like underscore linear, and then this will just be like linear. Right? Something like this. Layer. So that's not bad. I think we don't overthink it. I think that we do it this way, and I think this is pretty good. We'll be able to delete this linear layer accumulate in a moment, you'll see. As nice as is, think you may be worrying too much? Yeah, I think this is good. I was just not sure if like I wanted to add a tensor struct. I think it's good. I think I'm happy with this. So I'm off UK, have good coding. Thank you. I mean, the one thing is like if we had a tensor size, right? Like stuff like this, we would be able to have the size param come from there. That's kind of awkward, isn't it? The alternative thing that we could do here. Okay, here's another thing we could do, right? Do we really need this thing to work for different batch sizes? We don't need this to work for different batch sizes, right? What if we just made the batch size part of the layer? Right, when you create the layer has a specific batch size, and then everything should be good. Everything should be good, right? I'm trying to think if that's smarter, that's dumb. Sometimes I like thinking about these, like, design things, but sometimes I hate it. Because, like, no matter what you do, you're almost always going to be dumb, right? What would it look like if we made batch size a part of this? Well, the linear layer wouldn't have a batch size param, which would be cool. It wouldn't need an output param because we'd be able to just have it be part of linear, right? We could have like a nice allocator for linear. We could have like a make linear or whatever that is going to allocate us our output data. But things start to get very complicated very quickly. Like I can see down that path. But the thing is, if we don't do this, then it's going to be very complicated for us to actually implement any cool neural nets because we're going to have to keep around shit tons of different weight pointers and things. But maybe that's okay. Maybe I'm stuck on the PyTorch design, right? I don't know. It does actually seem kind of obnoxious to have batch size be limited. Like the layer to have to know the batch size. Hmm. I'm trying to think how I can avoid staring at this forever, because this is going to get very boring very quickly if I just have to stare at this forever, right? Like, it's tough because I don't want to have like a bunch of dynamic memory floating around. I like having the output buffers where it's static. Technically, I probably won't need to have batch size be variable. I might, but probably not. It is just very gross to have the batch size be part of the layer, though. Okay, let me think about, okay, so here's what, let me give you my thoughts, right? I can leave it as is, with no structs, nothing. And then what'll happen is when I have to implement like, CNN, LSTM, MLP for the MOBA game or whatever, it's going to be like 100 lines of allocations because I'm going to have to take all the different weight variables and stuff and I'm going to have to keep them around and I'm going to have to manually make sure I'm calling, each layer with the appropriate weights, right? And then there's also, if I'm going to read stuff from a file, right? If I'm going to like read from a file, it's going to be very difficult as well for me to, it's going to be very difficult for me to like write a function. It's tough to visualize what the code is going to look like, right? Okay, so the main thing, let me think about it this way. The main thing I need to do is I need to read a model in from a file, right? So we have a function that does that. It's right here. This gives you your weights. Technically, I could just return, I can just return right here. I can return this. And then your architecture. It's going to have to tell you the number of bytes or something. Yeah. You're definitely going to need something to tell you the number of bytes regardless that you need to be reading. So I'm going to just start coding on something here, and we're going to see if it's stupid, right? And you guys can tell me if I'm overcomplicating it. But I'm going to just, like, the dumbest, simplest thing I can think to do at the moment with my very limited capabilities here is to add output and add batch size, all right? We keep linear as is. Underscore linear at least. And then linear here takes a layer and it takes an input. It doesn't need to take anything else. Then this becomes layer output and this becomes layer batch size. So you have this very nice function signature. That is what this buys you. Okay? This linear layer accumulation is going to go away in a second. And then we're going to do I make one for relu? I think I do make one for relu. So we do struct type def struct relu in data. What is it? Float star data or float star? No, output. Int batch size. Int input dim. Okay, and then this is now underscore relu. This becomes data input float star output int size. Right? I less than size, and then this becomes output of I equal to f max input of I. Okay, and now we do void relu, which takes a relu layer and an input. And now it looks like this very clean thing, right? Where you take the input, you take layer output, you have batch size, and then you have input size. And the only thing that we need is this needs to be underscore relu, not relu layer. Dummy. And layer batch size times layer input dim. Sigmoid is just an activation. This does not need a layer. This is just defined for a single float. This is not a layer yet, since we don't actually use a sigmoid layer anywhere. And then this is going to be underscore conv2d. Let's make our we'll decide how we want to structure these in a moment. Type def struct conv2d. It's going to have float output, batch size, in kernel. Yeah, there you go. Then we do void conv2d, which is now just takes this, and it's just going to call the function. And then we have type def struct, and it's literally so brain dead that this can just be auto-completed. Right, it just takes all of our data. This is now underscore LSTM. And then we do void LSTM like this. Okay? And I think I want to group all this a little differently. Because I think I want like this at the top. Relu, linear, sigmoid. Comp2D. Because this is really the portion of the code that's actually, matters. And then I put the API at the bottom. Okay? So as I promised, right, literally this is 100 lines of code. Not even 100 lines of code. And then for the binding, so internal layers. We'll like do that, and then down here we do user API provided to help organize layers. I don't know, something like that, right? And then do I want all the structs or all of the impulse. I think I like it like this, which like struct implementation, struct implementation. I think this is good. This is very easy to edit like this. So we added, by doing this, right, we add 80 lines of code to have this wrapper. Actually less, because this thing is going to go away in a second. I'll put it up here for now, but this is going to go away in a second. So we add like, probably, what's that, 70 lines for this user API. And I think it's worth that. Yeah. And then we have load weights, and we have this main function like this, which we can now get rid of this main. This no longer is needed. Oh, and we can also do linear accumulate, right? We can also add linear accumulate here. Void linear accumulate. Wait. Is this actually valid? Hold on. I was thinking here that we could just zero the memory, but that's not actually efficient, is it? Yeah, that's not actually efficient. Damn it. Well, that sucks. We'll just do linear accumulate like this. And then we'll put this down to here until I figure out a better way to handle it. So maybe we'll find a better way of doing that, but for now, yeah, not bad. So 200 total lines. And then what we're going to do is we'll have this like load weights thing. We'll have a few other things, and that'll be good. Let me use the restroom real quick, and we'll test this. We'll make sure I didn't break stuff, and we'll implement the actual CNN LSTM layers, like CNN LSTM networks. Right back. Okay. It occurred to me that we also have to make allocators and destructors for these, right? Let me just look something up. I want to see if there's a style thing on this. I'm not actually sure that this answer is correct. Because now that I'm thinking about this, we'll go with this for now. I actually don't know if this is correct, but have you tried Perplexity? It can give you sources. There are not really any sources on that, though, right? It's like the actual thing that LLMs are intended for, which is a general amalgamation of knowledge from a bajillion different things. So this is what I was thinking for the make, right? Calicate. And then output is going to be this. So this gives you your sizes. And then you do void free linear. And then this is linear star. Star. What do we think about that? Allocate to your memory. We do make relu. And then this is like actually brain dead code right here. So this is very easy. Was it comp2d make comp2d? Just gonna give you all this garbage. Free comp2d. Yeah, and the reason we can actually tab this is hopefully just like this is actually brain dead if you're looking at it, right? The only thing I'm not sure about here is if we want all these different calyx instead of just like one big block of memory. But that's an optimization we could look at later. I mean, that actually gives you a pretty substantial API. Ask what is pufferlib. I mean, is it going to do anything other than just going to the site and then giving me this? This is actually pretty good, I will say. That's actually pretty good. I might consider using that. Right, so here are all the layers, right? Actually give you sources. Yeah, that's important. That's fair. I mean, I could see that replacing like traditional search engines just because the traditional search engines have become so garbage with all the ads. I'd always rather pay a subscription fee and just not have fucking ads everywhere. Always. Okay, so moba.c here. This has a bunch of stuff we no longer need. This is now in puffer, right? Yeah, but we need some of this. Hold on. Yeah, we don't need this. We don't need any of this. We don't need this. So this was the MOBA demo that we had from before, right? Let's make sure that this thing still works. Okay, now we include puffernet.h, and we go fix some puffernet errors. Type def struct linear. That syntax has always been weird to me. I don't even know if this is fully required, to be fair. I think I was just doing this because the Python layers are like weird about bindings. Might be able to clean that up. No member named Waits. Well, that's dumb. output star bias, output weights by. That's so weird that it didn't add that in. Okay, so that actually builds now. And now what we get to do is we get to init some puffernet stuff, right? So let us just net.h, go down to our user API. We need a few different windows here, don't we? Good. I think how I'm going to do this. I think we'll just grab the browser. Torch. We're going to try to implement this network now. Which is not a trivial network, to be fair. So we're going to have to do this piece by piece. Let's do type struct opennet struct mobanet. We're gonna do com2d star comp1 comp2d 2. We'll do relu1 linear star flat, linear star proj, and then was it linear star actor, linear star value function. All right. Interesting. See what it gives us here. Layer init. We don't care about the init functions here. We just have to get the dimensions right. Conv1 is going to be init. Let's see. So this is going to be num agents. In width is going to be 11. And height is 11. In channels, it's going to be 19. Out channels is 32. Kernel size and stride, this is now correct. Right? And while we're here, let's do comp2, which is num agents. 32. No, wait. In width, in height. Still. We have to compute this ourselves, don't we? I believe this was 3 by 3. Yeah, I'm pretty sure this is 3 by 3. Channels 32, 32, 3, 1. And then flat. It's going to be batch size num agents. Oh, I don't know why it does this. Agents, and then 26, 32. And then we have the projection, which is 64, it looks like. $32. Oh, hidden size 128. Size. And then actor is going to be hidden size, which is 28. Oh, we need num agents. 28, and then I believe this is 6. No, sum of self.action dimension. We'll need to find that. So 14, 17, 19, 21, 23, it looks like. We'll be able to verify all this stuff, so it's not going to be that bad. Agents, value function is 128, 1. So there are a few obnoxious things here, right? Like needing to know the conv input size and stuff like that versus computing it. It's not that bad, though. Yeah, that's what you would need like a tensor class for. So if we wanted that, we would need like a tensor struct. It's not that bad as is. Do we have multiple relus? There's an additional couple of relus here at the bottom, it looks like. And there's one hot. Quite a bit of encoding, actually, that we still have to get right. I mean, it's a substantial project. But at least this gives us our network. Now we'll have to load the weights in, which will be a pain. One thing we could do is we could make like we could make it have like a file pointer of some type. So like when you load in a file, right? You give the file to the init function. Something like that. Kind of complicated, honestly. Well, we need the forward function. Sure, we can have the free, and then forward. value function. This is not so this is not remotely what we need here. Layer. Oh yeah, this is fine because we get the output of the previous layers like this, right? So this is fine actually. And then the only things we needed are there are like a few different operations maybe that we didn't think about in the MobaNet. Let's see what it is. I mean, the big ones here are one-hotting the data like this. There's a little bit of pre-processing, which is no big deal. These concatenates, like, this is fine. This portion here is fine. But these concatenates are obnoxious. I mean, not really. I can implement a concatenate function. Let me just think about this network architecture if there's a better way of doing this stuff. Hmm. I mean, I guess you just have to, I just have to implement one hot and concat, right? Flatten, I actually don't need to do anything, I don't think. Yeah, flatten is, it's like the data is already flat. So I don't need to do that. But I do need to implement one hot and concat, I believe. I mean, that's not terrible. And then what'll this look like? It actually won't look that much more complicated than the Python if I do that, right? Yeah. What about this dot permute? Well, I'll just not implement it in the way that you need the permute, right? Yeah, dot permute is silly. Time is it? 5:18? I think I can probably implement these two and have like something of a network working in the next couple hours if I buckle down and do it. It's a little tricky. Let me make sure that I'm not missing anything. Dot split. What about the action selection mechanism? It's just a max, isn't it? Yeah, there'll have to be something for multi-discrete selection, though. I mean, it's literally puffernet dot h is what it is. It's just I need like more stuff in there. It's not a huge deal. I just have to implement a few more things than I thought I would. And there's not really any way around it, right? Like, you kind of just need all these ops. This will be a really sweet demo, though, if you think about it, right? Like, being able to run a net of this complexity in your browser, that's pretty sweet. So let's start on that. PM 1 a.m. stepping out. See you around. Thanks for dropping by. I want to make sure I understand how the one hot works in Python. Great to have in the background while working. Thank you. Put like the breakpoint right here. Oh, right. We had that issue, right? We should probably fix that. What the heck? Oh, yeah, we're gonna have some issues here. I'm trying to think what the easiest thing for me to do to fix some stuff here is. I think for now I'll just write a quick test. Batch. We'll do like 5, 3, 3, 0, 10. Like this. 533. Dude, why do I not know the API for this? Fuck. Low, high size. Okay, what did he do? Cool. F.1 hot. A 10 big. Okay, so it puts it at the very end, whereas you want it on the second axis, right? Always. Always on the second axis. So that's fine. Yeah, we can work with that. Input, output, batch size. Input size. Int input size. Int num classes, right? Batch size, input size. Yes. Oh man, the memory is going to be tricky here. But I think I can do it. It's going to be batch times. No, this is bad, right? Batch times input size. Batch times input size plus what was the first one? Num classes? No. The memory addresses for these are so tricky. Let's get batch elements, and then you have plus I times, what is it, input size times num classes, I believe. Wait, batch times input size times num classes plus I times num classes plus input what's the input address? There's also the input address to handle, right? which has to be not times num classes, batch times input size plus, is it just I? I think it is just I. Plus I, like this. And then I times num classes, this is plus input, yeah, in adder. So this was correct. Oops. Okay, and then you set the output address to 1. That should be 1 hot. Void concat. Cat dim 1. 1. 2. What size? 1. I can just do X and Y, right? And Y size. Is this correct? Let's see what it says here. Well, this code doesn't make any sense, right? It's batch times X size plus I, right? Yeah, this wrote some nutty code. The X address is just going to be batch times X size plus I. And then out address, not batch times X size plus I, right? It's batch times X size plus Y size plus I. And then here, Y address is going to be batch times Y size plus X size plus I. And then the out address is going to be B times X size plus Y size. Oh, wait. Hold on. No. Batch times Y size plus I is good. Batch times X size plus Y size. Now this is where you get plus X size plus I. So it was almost correct. I think that's right. So the way that you look at this, right, you go through the batch, and you have these two separate tensors. So you go through the first row, you grab all the x elements, which are b times x size plus I, and then you put them into, this is the row offset of your output tensor, plus I. So you put them into the first slots of that tensor, and then here, for the next one, the address index into Y is going to be the same, but then in the output, you also have to add the X offset because it slides over to the right. That should be right. And then we also need, didn't we need like a max or something? I believe there was a max operation that we used for snake. There's a max operation, right? Yeah, right here. And this will be float star input. Batch size. What is it? In float star. Int star. Output. Float. No. Int batch size. Int input size. For batch size. Index. Yeah, this actually is, this autocomplete was good because I have basically the same logic down here that I had already written. You get the first logit right, max index is 0. If it's bigger, yeah, this just duplicated my exact same logic here. And then output of b is equal to max idx. Yes. But now, the thing is, if you do it this way, hold on. This is not going to work this way, right? Because you need to have, this is going to be for multi-discrete as well. Yeah, this is going to be for multi-discrete. This is bad. This is actually trickier to implement than I thought. Let me think. So the problem here is that you can have a variable number of actions types that you want. I mean, I know how to do it. I'm just trying to think if there's a simpler way. We'll do it like this. Into batch size. Is this how you do it for a list? Something like this. Int inputs. So for batch like this, and then what we do is for yeah, like this. This is one of these cases, I think, where we want to have a an index that just keeps accumulating, right? We'll see. Logit sizes, yeah. So logit address. There's no way to get the logit address without just doing index because you have a variable number of size. So logit address put in address. And then the output address, that we can do. The output address batch size times num actions plus I. No. Plus yeah, it just wrote garbage code. This doesn't make sense here because you have to go over so this needs to be I less than num actions, I plus plus. Num actions plus I. This is the output address. And now what we do is float max logit is going to be the input of the in address here. This should be A, I guess. And I. Okay. We'll let this tab complete, and then we'll fix. So I actually like this implementation because it doesn't end up with anything super janky. You go over the batch, you go over the number of different types of actions here, your out address is going to be equal to the batch size times the number of actions. No, not batch size times number of actions. B times number of actions. Plus A. Yes. And then your logit here is going to be input of in address. Okay. I can just do in adder plus plus. No. In adder plus I, this is good. Max logic gets overwritten here. And then the output of output address gets set to I. And then you add the logit size of A. So int num action types. And this is num action types. Something like this. We'll have to validate all of this stuff. But that's not bad for a quick draft of 3 functions, right? One hot, cat and dim1, and argmax on multi-discrete. We'll have to make layers for these as well, right? Because we don't want to allocate the memory. These will tab complete though. These are super brain dead. Not MLP. Hi mate, can I know what you're doing? Yeah, so I've got this PyTorch net here. It's fairly sophisticated. It has linear layers, it has concats, it has one hot, it has CNNs, it has an LSTM in it, has a bunch of stuff. And I'm currently porting all of this stuff to work directly in C in like a little 350 line file, whatever this ends up being, so that I can compile this to WebAssembly and run it online. That is what we are currently doing. Now, I might have underestimated the complexity of this project just a little bit, but at this point we're mostly done, so it's not that bad. I mean, really, the only thing I underestimated was I forgot that I would have to add, like, these last 3 operations in here. But we'll test these. No worries. Let's just do type def struct one hot. Yeah, this is dumb easy. We can just tab complete this. It'll probably be right. I don't know why this is. Newbie in CS. Senior. Advise something can be helpful. It depends on where you're coming from and what you're trying to do. I can't just give like anything general that'll just help everyone in all situations, right? Okay. Yeah, we'll see if these autocompletes are correct. But okay, 418 lines. Now we ended up with a lot. Like, if you're brand new, you're gonna need to, like, there are some basics, like basic data structures and algorithms you will need to know. They're not going to teach you how to build stuff, but it will prevent you from doing a lot of dumb things. I mean, experience just building stuff is very important. I would advise you to not try to build stuff not around gigantic frameworks and tools that are like doing a lot of stuff. Like, try to like actually learn to build stuff. Try not to just learn a specific framework, I would say. Okay, we're gonna have to. But yeah, if you give me some context, I can maybe give you something more useful. Puffernet here. I think we just make the test for this already. DS and what is a DS? Is that a bachelor's or where should we connect? You're free to chat here. What is a DS? Oh, working on data structures in C. Okay, sure. Yeah, that's fine. That's what I learned. That's how I learned as well. Um, from there, let's see. I mean, from there you can pretty much already just start building stuff. Um, try building some like simple projects, like building most of the stuff yourself without using super heavy frameworks for things. It's a good way to learn. I will recommend to you. I mean, like, building simple games and things is a great way to learn. I'll recommend to you something I've been enjoying a lot lately. This is a really nice library for graphics. It's very low level, um, but it just makes it very easy to like. It's fun to work on stuff that you can actually see. But this will let you do, a lot of like heavy state and logic stuff. Right? Like, I've got like little demos that I've built with this where I have like pathfinding, for instance, where to like, you can just. Can I run it actually real quick? I don't know if I have it compiled anywhere here. Let me see. Here, let me see if this works. Walls. I think this maybe works. Yeah, cool. So here's like a little thing that I built. Like, this is a type of thing that you could totally build as somebody relatively new to CS to get some experience with stuff. Like, I built this cool pathfinder where, wherever I have the mouse here, it's doing pathfinding to my current location. And it's a nice little visual demo, so you can very easily tell if it's correct or not because you can see exactly how everything is pointing. It involves a little bit of, a little bit of algorithm stuff, a little bit of UI, a little bit of design in there, right? Things like this are fun. And these are a good way to learn. This took me like a day. But yeah, that's like the level of stuff I would recommend. $6.30. Good luck, man. Good luck. We want to add some tests here. So let's do Burnett, one hot, batch size, num classes. We need input size. We also, if I recall, we changed a lot of stuff, didn't we? Social account? Yeah, I've got a Twitter. Twitter's the main thing. Why do I have a million notifications blowing up? The hell's this? Yeah. Ignore Twitter. Gotta get stuff done. What the heck is this? Mixing C and Python. Okay, hold on. Here, I forgot I needed to fix a few things here. Because I need to test. Actually, shoot, I need to expose a lot of stuff, don't I? Well, technically, I could still test it this way for now. Yeah, I think I'm actually fine here. We'll do it like this. So test puffer net one hot. Input size equals what is this? 128. Num classes equal this. Then we'll do input is going to be make dummy data buffer one hot. Okay. Now we need to write the binding. X. Okay, we need to add these bindings here. Okay. We'll go grab the prototype from here. Where'd it go? I forgot the, hold on. Losing a little steam here, but we'll finish this today. At least I hope we'll be able to test like these functions today. Okay, so we have these guys like this. We also need to expose, no, wait, that underscore linear like this. Yeah, we want the underscores. Underscore linear like this. So we're just exposing the functional API for testing for now. I might regret that, we'll see. But okay. Now we need to put these things up here. Okay, so now we have all of our various different function prototypes or whatever. Puff1 hot. Now this should get it right. We'll see if it does. We can let this autocomplete. Don't need this. Sure. Cool. We actually have to get this thing to compile now. Cannot convert. Cannot convert float star to Python object. What? Oh. Okay, we actually didn't make very many errors. Where is this? Puff argmax. Oh, puff argmax. Int logit sizes. Oh, it just totally got the API wrong, didn't it? Size. Wait. No. Wait, multi-discrete. Oh, okay, it's down here. Int logit sizes. Yeah, you can't do this. This has to be like list logit sizes or something, right? Oh, no. You know what we can do? cnp.nd array logit sizes. That'll do it. Then we'll do int star logit sizes like this. Okay. So now we have all of the data types exposed from C to Python. Apparently this disagrees. Not be cast to pointers.data. Ay, 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 ay. Okay, I guess there are some errors in puffernet.h. So this is supposed to be A. .380. Flexible. Not at end of struct. Fair, you're allowed to do this. I remember now. Invalid use of. Do this first. Invalid use of flexible array member. Size of the entire structure is unknown. Okay. I didn't think I was doing that though, right? Malik. I know what we're gonna do. This is obnoxious. We're just gonna do this. Assignment to expression. Do I just mem copy it? Yeah, that seems to work. Net.h. What's wrong here? Argument is of type. Argument is of type int. Puffernet. Maybe I'm just using it wrong. No. In function, passing argument makes pointer from integer without a cast. What is the underscore? H underscore relu. Oh, you need the output. I forgot. I made it not in place. ND array output size. Expected 2 got 3. Do I have to adjust this prototype? Yeah, I have to adjust this. Output. Input. Implicit declaration of sigmoid. We'll look at that in a second. Undefined symbol sigma. Okay. Float sigmoid. Float x. Let me hold on. If I just do this, return type defaults to int. Float. Implicit definition of, oh, you just forgot to rename it. Yeah, we can leave it as exactly as is. I just forgot to rename it. And then buffer sigmoid. This is underscore sigmoid and underscore sigmoid. Compiles with no warnings. Now we have to edit puff relu. Sure. I can just pass it the same exact buffer. And it works. Cool. So we got this updated for the new API stuff. I'm gonna use the restroom real quick. We're gonna write the tests for the new 3 functions, and then I mean if we get that done today, I'll be happy because that will let us be able to write the full network. So I'll be right back. All right. Last few functions for the day. It's actually only 6:15. I do have an extra good hour and a half at least, so we should definitely be able to get this done. Okay. Test buffer net. Cat. Dim1. Batch size. Batch size 16. X size equal 32. Y size 64. XNP. Okay, we have the outputs. We do cat. Y output batch size, X size. Perfect. And then output torch. We assert near. Breakpoint. Cat dim1. And then argmax multi-discrete is going to be a little harder. Def test. Multi-discrete. Batch size. Logit sizes. This is equal 5, 7, 2. Okay. Okay. Make some of this, sum of logit sizes. Input P is going to be logit sizes. That's good. Logit sizes. P.array logit sizes. Dot sum. Num actions. Length of logit sizes. Okay, and then what we do is output puffer, batch size num actions, and when we argmax into it with batch size logit sizes num actions, input torch. This argmax here does not actually work. So then we have, yeah, there's not like a good thing for this, right? I think we have to do action slices torch.split equals torch.stack of argmax, and then we output torch attach torch output puffer. Break. And then we add these to the tests. Test buffer 1 hot, captain 1, and we will, just to make these tests a little faster, comment this out while we're testing. Python only applicable to index tensor. Okay, fair play. Make dummy int data 10. Yep, this is fine. Int data. Logit sizes. Oops, this is not the function that I needed, right? Make dummy int data num classes. Oops, should be like this. Num classes. Num classes. 0 classes. Yeah, classes. Perfect. Only applicable to index tensor, huh? Okay, so it looks like it's segfaulting here, right? Yeah, okay, so our actual implementation segfaults, cool. Shape, input, shape, input, see. Cool, and 32. Let's see what we're doing here. Buffernet pi x. Float star. Well, this is not float. This needs to be int star input, right? These are ints. And then 1 hot. That's the problem. And then I assume that I did the same thing in here somehow. Yeah, this is int star input, int star output, right? And then we have int in address, int out address. Perfect. Okay, what happened here? Buffernet 347. Yeah, okay, so we forgot this needs to be int star input. And yeah, that's it. Passing. Output, right? So this output needs to be size of int. And then output here needs to be int star. We're going to use ints instead of longs here. Okay, that compiles. Test. Do we still segfault? Buffernet. Yeah, so we're still segfaulting here. .c. Oops, that doesn't work. test. Okay. Let's just go grab the API and figure out where we're segfaulting, right? Batch size is 16. Input size. Class is going to be 4. We'll do make 1 hot layer. It's going to be make 1 hot. And we'll do 3 1 hot. 0. Then we'll do 1 hot layer input. And then we'll do int star input is going to be calec. And classes. Cool. And what do we do? We'll just do like test puffernet sh puffer clang g-o test at puffernet test puffernet dot c, and I should not need any of this stuff. Okay, puffernet.h, wrong, goes here. And now I get real stuff, so we have to include standard IO, all this crap. You need string for memcopy. I always forget about that. Okay, so test puffernet. This actually runs. Test puffernet. Still segfaults. Why does it segfault? I do not know. Let's see. Well, wait a second. Does it even segfault in the same spot? Let's just make sure of that. It does still segfault on the 1 hot. Okay. So, yeah, I had this breakpoint there anyways. No, this is a cat breakpoint. What? Okay, yeah. So it segfaults here. Takes input, right? Then takes output. Well, this is wrong. This is input size num classes, right? Okay, we don't get the segfault anymore, right? We just get an error. Shape. Torch. Did I do this wrong? Okay, this needs to be longed or whatever. Somewhat obnoxious. Long. Dot int. Attach. Insertion error. Point. Max out. D-type float. Int 32. Ooh, look at that. We got it. Okay, we have our, whoops, we have our one hot function. That's a one hot function. It's a one hot function. Does this cat dim one just work? I think it does. I mean, I'm sure we'll find some bugs later, but... Okay. Nope, it doesn't. Okay. I was gonna say, that would have been too good to be, possible. Put torch shape, p output, upper shape. Okay, so it did something weird. Did something real weird. Neither of these make any bloody sense, right? Oh no, wait. This one is just working. Yeah. Shape. This is just dim equal 1. Torch dot shape. Torch output buffer. Okay, we still have assertion error. Output buffer. Torch. Completely different, right? Input. Put buffer 0. output torch 0. So we said that this is 5, right? 0, 1, 2, 3, 4, 5. No, wait, this is 5 here. So the best one is 1. So they're both right. And then the next one is 7. And it says 6. So torch is correct. And then 2, 0, torch is correct. So let's go to our source. Let's go to our source. Action types. So this should not even be possible because it's not just picking the wrong entries, it's picking like completely invalid ones. Out address. Logit sizes of A. I less than num action types. Interesting. Output of out adder is equal to I. Then in adder gets plus equal num action types. I don't see anything wrong with this. I'm obviously missing something. I'm also starting to get quite hungry. So I have to order some food soon. Batch size, num actions. Yeah. And then max logit is going to be the input of the in address. define action types to logit size, yes. Then the output to the input in address plus I. It's bigger than the max logit. Set it to the max logit, and then you set the out address to I. This looks good to me. Let me see if I mess something up with the data. Uppernet. In 32. Well, hold on. Maybe I screwed this up, right? You should be able to see right here. Logit sizes. B type. Aha! Good over you. It's always that, man. Always, always, always that. I should add some asserts or something. Maybe we'll make like a safe API or something for the testing. Because it's always... Puffernet. It does concern me a little bit that it takes that long to run. There might have to be some optimization done. We will see. But it does run. Well, maybe not, because I'm importing PyTorch, and PyTorch takes like a good couple seconds to import. Okay, so we literally have all of this done in C. Let's add this before I lose it. .h net-m new puffernet layers branch dev add test puffernet net more puffer test. We like puffernet. So I'm happy with that progress. What I'm going to do now is I'm going to order my dinner on the side, and then while I'm waiting for my food, as long as it takes to get here, as long as it takes for my food to get here, I will try to get the full network working, and we'll see how that goes. But I'm very, very happy with this progress. Like, this did not exist, right? This is a 400-line file that just does neural nets for you. Also, let me check a DM. Nope. Nothing looking. Lots of progress. Just got here. Yeah, let me order my food. We're still going to work on this for a little bit. I just need to order something before I pass out. Technically, if I were really grinding this, I would just eat food on stream and keep working. But I think what's probably going to happen is I'm going to just order something, eat, and go to bed early. Because tomorrow, I have another environment, another big environment that I've been working on off stream that's still secret. And I'm going to try to port the whole thing to C tomorrow. It's like about the same size as the MOBA. Yeah. You figure out what the hell to order. Let's do this. It's a good protein. Yeah, it doesn't matter. So I'll tell you the progress real quick. I'm pretty happy with this. So look at all the layers that we have implemented. Relu, Sigmoid, Linear, Conv2D, LSTM, OneHot, Concatenation, and argmax multi-discrete sampling. We also have a user API around all of these that just manages like all of the variables for you here. So this is like closer to what PyTorch would be. It's actually pretty much almost one-to-one with PyTorch. It's a little bit lower level because we don't have a tensor class or a tensor struct. So it's a little bit lower level because you have to manage stuff like batch sizes and like conv dimensions. But it's pretty close. It's only 400 lines of C. We have a very nice test for this. So here's your 160 line test, and this actually ensures that our version is exactly the same as PyTorch. So not only is it correct, but it matches PyTorch exactly, meaning that we can load from PyTorch into Puffernet. This is what I've been doing. I think that's pretty cool. Test cases took by surprise. Glad they're there. Yeah. These are good. They're a little bit annoying to write because, like, in order to do this, I'll just show you what I had to do. There's also a puffernet.pyx, which has this binding. This is an intermediate layer between C and Python. So this has to exist. But given that this does exist, it's not bad. Okay. Now what we're going to do is what we were doing before. We were trying to do this MobaNet. So there's this piece of code that I have. Let me go find it. Speaking of which, how are we doing on stars? 13 stars off of 1K. No, wait, it's right. Head is stopping working because no food. Need food in order, think. Torch. Okay, so this is the network that we're trying to implement. We're going to at least see if we get a first pass on the logic today. So the first thing is that this is net one hot. It's going to be init one hot. Not like this. It's 16 dimensions, right? 16. Buffer net.h. One hot. Batch size, input size, num classes. This is batch size, 11 times 11. Num classes is going to be 16. Okay. And then we have to do net map stack. Times 11 times 16, right? Three. So this is the map stack. Okay, let's see from here. So this goes on forward. What you do is you're going to one hot Jeez, this is so obnoxious the way that this is. I really am going to have to mess with the observation format or something to make this easier. There are just like so many tensor slice and copy and operations and such. They're very difficult to do well. To be honest, like, I almost want to spend some time making that net better because that's actually kind of slow now that I'm looking at it. Yeah. Well, we're very close here, though. Let me check one thing. Just grab pairing. Okay, so we still have like a good 20 minutes. Let me see if I can figure out some optimizations to this network. I'm gonna draw this as well, so it'll be like kind of interactive. We'll show you some cool stuff. Draw a line. Okay. So the way that it works right now, right, is if this is the observations, this is 26 extra. And then here, what we have is like $11 and by 4 map is it's encoded flat here. And then what you need to do is you get, so this turns into 11 by 11 by 4. So what you end up getting is you get this map feature here. And then you get this 3 map features like this. So this is one hot, and then this is norm, and then you do cat. One hot means that you take, let's say that you have a vector, or let's say that you have a value that is 5, right? And you have 10 total options. Then what you do is you make a vector of length 10 and you set the 5th one to be equal, or you set, I guess that's the 6th one technically, to be equal to 1. So it's essentially you treat the data as an index which tells you which element to set to 1. Yeah. But I'm doing like tons of bullshit here. So then what you do is like the flat features. This gets normed. And then like proj cat. These two get catted together. And then from there it's easy. But that's too much stuff. It gets normed so that the sum is 1. It just gets divided by a fixed value. Cat is concatenate. So like you stack all the stuff together. So basically what's happening here is I just have too many freaking operations on little slices of data that are going to drive me nuts the way this is written. And not only that, but this is not efficient the way it's written either. It does not get normalized so that the magnitude is vectors 1. That's not the only type of normalization, right? In this case, I'm just dividing by 255. Because what I'm doing actually here is I'm storing all the data in 1 byte, which means you don't get a lot of precision. So if I have a variable that's from 0 to 1, what I do is I multiply it up by 255, and then that gets cast to a byte, and then I divide back by 255 and cast as a float. So I get to store it in 1 byte, but I still get a little bit of precision associated with it. So there's a little bit of a trick going on there. But I can see looking at this that there are like all these operations that are slowing this down, and this needs to be faster. Really, the main problem here is the fact that you need to one hot this, right? But there's not really a good way around having to one hot it either. Yeah, the thing that's just really obnoxious is like the write patterns here. They don't match up. Like there isn't an easy way to just do a one hot plus a concat plus like all these things in one step. It's difficult. Hmm. It's tough because we don't have like the notion of applying an operation along an axis. Like the main thing is I'm using array ops here. And I'm using array operations in like I'm using array operations in kind of a tricky way. I'm sure this is not efficient anyways, right? Like we should be getting 1,000,000 steps per second and we're only getting 500K. But this is difficult because like the thing is like if you just look at it visually, you say, "Oh yeah, just stack it," right? But the thing is it's not that easy because the way that these things are laid out in memory, certain operations are easy and certain operations are hard, and this operation is hard to do nicely. Yeah, not to mention all the casts and stuff that are getting done. What is the basis case? Like if we have one observation, would make looking at it doesn't really help if you have one observation even. Like the thing is that there are a lot of operations going on here, right? And like it's inefficient in this implementation, so we need to make this more efficient. And if I can find a way to do that, the hope is that it'll make the C easier as well. Um, because like what's happening now is we're splitting out the data into 3 separate chunks, and those chunks do not occupy contiguous memory. They're contiguous along certain views, but they're not actually contiguous in memory. And there's not really a way to make them contiguous in memory because of the way that batching works. That's like a hard issue, though. There's not really a good way around that one. So we have like essentially a split along axis operation, if you will. It's actually a little worse than that. It's like there's a bunch of reshapes that have to happen before you can even do that. And then you have to apply a one hot, and then you have to apply a stack along an axis, and then there's a concat, and then you can get normal stuff happening again. And there's got to be a way to simplify this. So basically, the operation that we're trying to do here that we care about is we have one filter that needs to get one hotted, we have some extra filters that don't need to get one hotted, and then we need to be able to conv over the stacked versions of those once we stack them all together. Um, it's difficult because like hmm. I mean, there are technically other encoders I can use for this instead of one hot. One filter to hot one, extra to not hot one. There's quite a bit of stuff. So there's one filter here that needs to get one hotted. there's several additional filters that need to get just stacked on top of this one hot. And then I guess we also have some flat data at the end. This is going to take some thought. Stacking filters, then flatten. Yeah, you can do all of that, but it's going to be like, one, it's going to be me writing a lot of C to make the same thing work in C. And two, like the way that this is written right now, like there's just a lot of copying data around here. Like every time that you take a slice, every time you have to take data along a slice, that, okay, you're fine doing that, but as soon as you do anything with data that is not contiguous, you end up having to copy it. So like I think we're copying the data several times here, which is really bad in this little network. Reference the data. Well, the problem, like, yeah, you can reference, but the thing is it's not in contiguous memory. Like generally it's like, okay, fine, your data's not in contiguous memory and there's no way around that. Fine. Then what you want to do usually is you want to get it in contiguous memory and do all your operations there without having to do any more copies. Why can't we get it to contiguous memory? Well, if you look at it like the way that I wrote it up here, so each of these little slices here is one of the filters, right? We have like 11 by 11 map filters. So we have like flattened filters here. I guess there'd only be 4 of them. But yeah, 11 by 11, 11 by 11, 11 by 11, 11 by 11. Um, so technically, is that the way it works? Hold on. I guess technically we can just split it, right? I guess technically it looks like this, where this is like 2D continuous, and this is 2D discrete, and then this is extra. But like just because I can split it like this doesn't mean it's contiguous. Right? You like the split operation itself. Like the memory doesn't know that, oh yeah, this is a nice block. Right? You're still like, this is a row, this is a row, this is a row. It's not contiguous. Yeah, each slice is a the slices are contiguous, but the thing is you don't buy like, just because the slices like they look like they're like contiguous like that, it looks like they are, that doesn't mean they actually are. Like what contiguous memory is, like here, this block here, this is a contiguous block of memory, right? Like this is a contiguous block of memory, right? This is not a contiguous block of memory. You know what I'm kind of leaning towards? So, I mean, this is going to be a whole bunch of additional custom operations still. But, like, what we could do is we could take this block here, this one hot block, and we could just, like, allocate extra, essentially. So, like, this is what your one hot looks like. This is what your one hot tensor looks like once it's expanded. We could just, like, allocate extra here, and then like this goes here, and then this goes here. NumPy flatten allows us to make it contiguous. Yeah, but you have to think about how that happens, right? That's a copy. So every time you look at an operation like that and say, oh yeah, that lets us do it, like I have to, not only does that incur a copy, which slows down our training code here, that's slow, but also I have to go implement that in C. Which is fine. Like I can implement some C stuff, but ideally I'm not implementing like a bajillion different things. I think I can actually cheat this because I'm thinking right here, if I just make this F1 hot here, if I just make this dimension 19, so I just cheat some extra layers in, then what I can do is I can take these extra map features and instead of doing this concatenate, I can just like, instead of doing this concatenate, I can just like put them in there maybe. Does that work? I think that works. Yeah, I can just put the extra ones at the end there, which would be faster. Slightly easier. I actually don't know that if that is even easier. I mean, I probably need to implement like a slice operation and a couple other things, right? This one hot is just so obnoxious. Like if I'm thinking about it here, right? Without the one hot, this is easy. Without the one hot, this is super easy. Or alternatively, without the extra data, it's also super easy. Food's almost here. Yeah, I think my brain is gonna have a tough time until I can think about this better. I'm gonna definitely be thinking about this though over the weekend. I have some other stuff to do, but I'm gonna be thinking about this for sure. Yeah, I need to get some food. I'm looking. Maybe this type of encoder is just not a good idea, right? I thought that this was a good idea, but maybe it's just not a good idea to have mixed one hot and continuous data. Yep, that is what a one hot encoder does. It is true. Well, I'll tell you what. I'm gonna be back on Monday. I'm gonna work on a lot of cool stuff over the weekend. I'm gonna get stuff into a very nice spot. Um, I if you'd like to take a look at some of the stuff that's in Puffer at the moment, it's all open source. So we've got, and really this is 12 stars away from 1,000. So if you want to support the project, if you haven't started already, please go ahead and help us with that. It's been great to see the growth on this. It's really awesome, and we're very close to that 1,000 that milestone. This is all open source, and the other thing is there is a Discord, and there's a lot of stuff going on in there with contributors and whatnot. Um, like a lot of the stuff I do, you can ignore all the C that I do if that's not your jam, right? Like we have much easier ways to implement ultra high perf RL environments and to learn a lot of stuff around here. So if you're interested in that, slash puffer. Yeah. Check that out there in the Discord. Um, feature hashing embeddings. Other encoding types. Possibly. I'd have to look at specifically this and I'll think about some stuff. But anyways, I'm gonna go get food. Thanks, folks. I'll be back on Monday with some cool stuff. And yeah, I think next week we're gonna have like this nice full standalone PufferNet library. We're gonna have demos running on the web. We're gonna have the MOBA running on the web. We're gonna get training working, and we're gonna have like models just being imported to like the web version very frequently. And we're gonna start having more environments as well. So thank you everyone, and I will see you around.